See more students are joining. So basically the way it works is, imagine you have a sequence, right? So imagine you have a sequence like this, like for example, an is equal to 3an minus 1 plus, for example, or minus, let's say plus 2an minus 2, right? So you have a sequence that looks like this, right? So then the question is, you want to figure out like, what is the formula for this sequence? So for example, maybe I give you two starting conditions, maybe a0 equals 0, maybe a1 equals 1, right? Or maybe, I don't know, maybe different starting conditions. Instead of 0 and 1, maybe we had, 2 and 5, okay? So maybe this is 2, this is 5. And then what you do is you take 2 and 5, you plug them here, and then you get the next one. So 2 and 5 is going to be 10 plus 15, so you're going to get that 8, 3 is going to be 25, right? And then what you do is you can again like plug in a1, a2, and then you get a3, and then you plug a2, a3, you get a4, right? So basically we have sequences like this. These sequences are called linear sequences. So let me clear this. So let me just like write it down. So this is called linear recurrence relationship, right? Relationship. Why is it like a linear recurrence? Well, because it doesn't have any square or cube terms. For example, if I were to have like a square root here, maybe like a squared here, or like a cube here, then this is like wouldn't be a linear recurrence anymore, right? Because it wouldn't work. But if all the powers are 1, so basically the next term is made out as a linear combination. So the next term is a linear combination of the previous terms, then it's called a linear recurrence. Okay, so what can we do with this? What can we do with this linear recurrence relationship? Well, we can solve it. And normally what we want to do is we want to find the formula. So for example, I want to like figure out, what is going to be the formula for an. So ideally, I'd find the formula like this, that an is going to be, I don't know, like maybe square root of like 2 over 3 times like, I don't know, like 5 to the power n minus, for example, 7, 3 to the power n minus 1, right? So for example, if I find the formula like this, if I were to get this formula, if I were to tell you that, hey, an is going to be this, and this thing satisfies this, then this will be done. And if this satisfies this one and this one, then this is great, right? So basically what we want to do is we want to solve the linear recurrence. We want to figure out, okay, what is the formula? How can I get from like this relationship to something like this? Well, now this is not certainly not the right formula in here, but I'm just giving you an example. What you want to do is you want to come up with a formula, right? Like you have this something that's something, you can compute it like one by one, but you want to come up with a formula that's something that's going to look like this, where you can basically just plug in n, and then you can compute the stuff and get the final result. You don't want to like, be computing all the terms. Maybe you just want to compute the 1,000th term. Then you don't need to, keep in memory, okay, what is all the terms between 1 and 999. You can just plug in n equals 1,000. For example, in this formula, you take n equals 1,000, right? And then you take it and you plug it in here, and then basically you're going to get some sort of formula. So this is what we want to do. We want to figure out what the formula is. Now, before I go ahead and basically like tell you how to compute the sequences, let me motivate this a little bit. Like, why do we even care about these sequences? So, well, one thing is you can certainly get an AMC question where they just give you like the setup like this. They give you two terms and then they tell you, hey, this is the relationship for the next term. And then basically figure out what the formula is. Or they can ask, figure out what is going to be the term that's like 1 billion, right? In the AMC 12. So now if they ask you to compute the 1 billionth term in the sequence, and they told you the first two, obviously you don't want to compute them one by one, right? If they ask, compute the fifth term, then you can compute the third, the fourth, the fifth. It's going to take you 1, 2, 3 minutes. You can do it, right? Even if they ask you the 10th term, you can probably spend like 10, 15 minutes compute it. But if they ask you, the 1 millionth term or like the billionth term, obviously you're not going to write down like a billion numbers, try to compute them one by one, right? You'd want to like use some formula like this, where you just plug in n equals a billion, and then you calculate, and then you get something, right? So this is kind of like the main idea. Now, where do these linear recurrences show up? So it turns out that oftentimes when you get a problem, you might not even get this equation here. You might get like a problem which when you solve the problem, you're going to get an equation like this, and then you're going to have to solve this equation. So let me maybe motivate this a little bit. So I have some, PDF links here shared with you guys. So I'm going to send you all the links. So let's look at, like, for example, this problem in here with recursion. So, okay, there's a famous example, which is the Fibonacci numbers, right? So you guys know the Fibonacci numbers, 0, 1, and then the next term is going to be the sum of the last two terms. So basically, if you compute F2 is going to be 0 plus 1, which is 1. And then if you compute F3, it's going to be 1 plus 1, which is 2. So Fibonacci numbers is, for example, like a linear recurrence as well. Now, I'm going to share this PDF. Let me put this PDF here in the chat with you guys as well. You can basically, click on it and you can download this PDF and work, for examples from here. But let's look at like this problem 10.1. So what is going on in this problem? So basically, what do we have? So we have a bunch of, disks in here, rings. And then what we need to do is we need to take these 8 rings and then move them on the other side. Now there is a rule. So one thing you can do is you can take a ring. So basically, first of all, when you move the rings around, you need to start with the smallest one from the top one. So you can start with the top one and then you can basically put it here, right? And then what you can do is you can take the medium one and then the medium one, you can put it here. Now there is one rule. You cannot take a bigger ring and put it on a smaller ring. This cannot happen. This is not allowed. But what you can do is you can take a smaller one and put it on a bigger one. This one is fine, right? Okay, so like if you, for example, you can always take a smaller one and put it on a bigger one. You can never take a bigger one and put it on a smaller one. Okay, so that is basically the rule. So if you look in here, if, for example, I moved now, if you look at this one has two options. You can either go here or here, right? Because the smallest one, it doesn't have any restrictions. This one wouldn't be able to go on top of this one could only go back. Or another thing you could do is like if I were to look at this one, the third one, where the third one? Well, the third one, I cannot put it anywhere, right? So if I wanted to move the third one, then basically I would need to take the small one, move maybe the small one here, and then maybe take the third one, and now the third one's gonna be here, right? Something like that. So, okay, so this is basically the question. So now the problem is asking basically, if I have 8 rings, what is the smallest number of steps to move all these rings to like this problem or to this tower or this tower? So this is called the Tower of Hanoi problem. It's pretty famous. You probably have even seen like the physical problem when you're like kids, you go to like some sort of like math camps or like brain teaser problems. You often have this problem. So the question is, like let's say that I have n disks and n disks or like n rings. So what is the minimum? So what is min number of steps? Minimum number of steps to basically move all n of this, to move them, for example, here, such that you have, the biggest, the second, right? So basically, what is the smallest, the minimum number of steps to basically move all of this to here? Obviously, you cannot move 2 or 3 at once. You can only move them one by one, right? So let's say that, the answer here is going to be an. So basically, an is the answer for the problem with like n rings, right? So then we basically want to figure out what an is. So in our case, for example, they're saying that we have 8 of them. They're saying that, we start with 8 rings. So they're saying that n equals 8, right? So in this case, the problem particular is asking a8. But this is going to be a8. But, more generally, what is happening if, you have like any arbitrary n, right? So the question is what is happening for 8, but then also what is the general formula for n? So what is an? And in order to solve this problem, what they're suggesting, and I guess like it's pretty reasonable, is to ask, what is going to be the problem for 1, 2, or 3 rings? So basically, what is a1 or what is a2 or what is the answer when you have 3, right? So basically, you're trying to solve a smaller problem. So instead of solving the big problem, you can attempt to solve the smaller problem, right? So the smaller problems usually are very easy. So for example, if you were to have just one ring, right? So n equals 1. Well, how many steps it takes to move this ring here? Well, it's just one step, right? You just made one step and that's it. So basically, a1 is going to be 1. If you have only, one ring and you want to move it, it's just going to be one step. Okay, so now the next question is like, okay, if I have 2 rings, how many steps do I need when n equals 2? So if I have 2 rings, so if n equals 2, how many steps? Well, clearly I want to move this in here. Well, before I move, this one here, what do I need to do? I need to move this one here, right? So basically it's going to be, like this is going to be one step. And now I move this one here. So it's going to be the second step. And now what I do is I move this one back. So it's going to be the third step, right? So basically, you guys see there's like 3 steps in here. 1, 2, 3. So basically a2 equals 3, right? So if you have, if you had like 2 rings, you would need 3 steps. Okay, so that's cool. So we did this one, we did this one. So now the question is, okay, what's happening if the number of rings keep increasing? So let me maybe write it here. A1 equals 1, A2 equals 3. Maybe we're going to notice a relationship. That's what you usually want to do, is like you want to notice if there is a relationship here. So far we have 1 and 3. So if I had 3 rings, what would happen if I had 3 rings? So basically 1, 2, 3, right? Okay, so I have 3 rings. So what would happen? How would I move them? So basically I want to take this and I want to move it here, right? So I want to have the big, the medium, and the small. So how could I do that? Well, one thing you can ask is, okay, what's going to happen when you have the last ring? Well, eventually, whenever all of this move here, what am I going to have? Well, at some point, this one, the last one, is going to need to move here, right? But when the last one moves here, what is happening when the last one is moving here? What can I say? Well, if the last one moves here, it means there is nothing on top of it, and it means there is nothing here. So it means that all of this all of this would need to be here, right? Like the minimum and the small, they would need to be here. So all of this would need to be here. I can move the last one. And then after I move the last one, basically I can take this block and then I can move it back here, right? So we're going to have the smallest one and then the medium and the small, right? Does this make sense, guys? So basically, what you can see is you can see the answer right away, that basically you're going to need one step here to move this one. But then how many steps do you need to move the two of them? So now this is actually the previous problem. The previous problem tells us how many steps we need to move two of them. The number of steps is going to be A2, right? And then in here, what is the minimum number of steps to move two from one side to another side? Again, the minimum number of steps is A2. So what I get is I get a linear relationship between, like if I wanted to compute A3, how many do I need to move 3? Well, I need to move A2 and then 1 and then another A2 steps, right? So basically, you see that A3 is going to be 2A2 plus 1, right? So basically, this is the relationship that we were looking for A3. So if you plug in the numbers, if you take this 3 and you plug it here, you're going to get what? We're going to get 7, right? So basically, A3 is going to be equal to 7. Because you plug in 3, so 2 times 3, 6, plus 1, you get 7. So basically, you need 7 steps in total. But now what is interesting is that the same solution works for, like not only 3, you can have the same recurrence for like any number n. So basically, okay, so let me clear this maybe a little bit. So we got A3 is equal 7. So you can think about it more generally, if I were to have n rings, right? So if I were to have n rings, so this would be the last one. So this would be the last ring. And then there would be, like basically a bunch of like other rings in here. There would basically be in here n minus 1 rings, right? So what is happening when I move the last one? So if I wanted to move all of this, I want to move all of this here, right? If I want to move all of this, eventually at some point I have to move the last one. You see the reason I look at the last one, because the last one has the most restrictive, like the smallest one, you can move it wherever all the time. It doesn't care, because whenever you're going to move it, you're always going to put it on something bigger, right? It's the smallest one. So it can go wherever. The problem is with the biggest one, you cannot take a big one and put it on a small ring, right? So because it's the biggest one, you can only put it on an empty slot. You cannot put it on like some other slots that has other rings. So that's why it's special. So that's why you look at it. And well, obviously, if I were to move the entire thing here, what needs to happen first? Well, eventually, I need to take the biggest one and I need to move it here. Well, this is going to be one step, right? Well, if I did that, what's happening next? I have n minus 1 of them. So when the last one was moved here, where does this needs to be empty? It cannot be here. So all of this, they need to be over here, n minus 1 of them, right? This group in here, they need to be here. Well, and then after you move them, you'd want to move this group back here. So you'd want to move this group of n minus 1 here. So the question is, how many steps does it take? Well, obviously, what's the smallest number to move n minus 1 from one side to another side? Well, it's the previous problem. It's going to be a n minus 1. And well, again, I need to move n minus 1. I need to move all of them here. How many steps? Again, a n minus 1. So you guys see, we get a relationship. So there's a relationship. If I wanted to move n of them, then the answer would be an. Well, then it's basically the answer for moving n minus 1 times 2. So it's going to be 2an minus 1 plus 1. Does this make sense, guys? So basically, okay, we kind of like did this one and we did this one. And then for this one, what you can do is you can plug in the numbers. You can plug in, so you can compute A4. So if I wanted to compute A4, this would be what? This would be, 7 times 2, 14 plus 1. So this would be equal to 15, right? And then, if I wanted to compute A5 would be double this plus 1. So it would be 31. And then A6 double this plus 1. So it would be 63. And then A7 double this plus 1. It would be 127, right? And then A8 double this plus 1 would be 255. Right? Does this make sense, guys? You see what I'm doing here? So basically, these numbers, they started growing really, really fast, right? By the way, what is one thing that you notice in here? What is one thing that we can notice about like all these numbers here, like 1, 3, 7? Do you notice a relationship? 1, 3, 7, 15, 31, 63, 127. Look, the answer is also kind of like hidden in here. If you look at this too. Basically, what this is saying is that like at every step, it like almost doubles. It not quite doubles, but it almost doubles in a sense of, the number is going to be doubled plus 1, double plus 1, double plus 1. So it kind of like makes sense that maybe the answer is going to be a power of 2. Right? And then actually, if you look at these numbers, they're not quite powers of 2. It's 1, 3, 7, 15, 31. But there is an easy way to make it a power of 2. You can come in and you can add a plus 1. So if you do 1 plus this, 1 plus this, 1 plus this, 1 1 plus this, 1 plus this, 1 plus this, 1 plus this, 1 plus this. What do you see? You see that all of them are going to become powers of n. It's going to be powers of 2, 2, 4, 8, 16, 32, 64, 127, right? And such and such and such. So this is basically 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So basically we get that if I were to do 1 plus an, this would be, 2 to the power n. Right. So if I wanted an, this would be 2 to the n minus 1. Okay, but this is kind of like just a guess. This is like me guessing that, okay, if I add plus 1, then I get powers of 2, but I haven't proved it. I just like noticed the relationship. Maybe this relationship is not true, but at least it's satisfied until the case AA, right? So we need to prove that this relationship is true. So basically what we did is we solved the recurrence relationship. We didn't solve it, but we just guessed that an is basically the power n, right? So this is basically, the motivation is that you have a problem like this that doesn't look like a recurrence problem at all, right? You have this setup that you need to move like rings from like one pole on another pole, right? And then what we did is we noticed that, okay, if you wanted the minimum number of steps, it's basically the big problem is a subcase of like, it's like basically the smaller problem modified a little bit. So that's where usually the linear recurrences happen, is that you have a big problem to solve. You need to figure out what is the answer for n, but it's very easy to figure out the answer for n equals 1, n equals 2, n equals 3. And then another thing that you notice is that, if I wanted to solve the problem for n, then basically I can look at a small problem. I can look at the problem when there is only n minus 1 of them, or n minus 2. So if I can use the answer from n minus 1, from n minus 2, combine them in such a way to get the answer for an. In this case, you see that if you wanted an, you only need the previous problem, but it could be the case that you'd have something like this, where the next problem would basically depend on, okay, what is the answer for, n minus 1 and what is the answer for n minus 2. So you need to combine the two of them with like these coefficients, 3 and 2, for example. It can be any coefficients, right? It doesn't have to be plus, can be also minus, as long as the relationship is linear. So basically you get that an is going to be a linear combination of all the previous terms. It could be plus, minus, the coefficient can be whatever, but it's a linear combination. If that's the case, then, we are fine here. Okay, so any questions about this? No? All right, so I guess, let's kind of like try and solve this problem. So let's look at, so how can we usually, solve this problem? So if we look at, for example, the Fibonacci problem, right? So you guys are probably well familiar with the Fibonacci problem. The Fibonacci sequence basically said that if you wanted to compute, an, then an would be basically, an minus 1, the last two terms, an minus 1 plus an minus 2. So if, for example, I wanted to, guess what's going to be the formula for an? Well, first of all, you need the starting condition. So you need to, know what is A1, what is A2. So you basically can write down A1 equals, so actually you can start even with A0. So you can say that A0 equals 0. So A0 equals 0, A1 equals 1, A2 equals 1, and then A3 is going to be the sum of the last two. So if I sum them, I get 2. And then A4, again, sum them, I get 3. And then, A5, sum them, I get 5. A6, so A6, A7, A8, A9, A10. So let's see what are going to be all these numbers. We're just like writing down some numbers to maybe notice a relation. Remember in the previous problem, we noticed that if I added plus 1, those are powers of 2. So kind of like, makes sense, what is going to be going here. Well, and I guess we do see A6 is going to be the last sum of 2. So it's going to be 8. And then what about A7? A7 is going to be 8 plus 5, 13. And then what about A8? So sum the two of them, so you're going to get 21, and then sum this two, so you're going to get 34, and then sum this two, so you're going to get 55. So what do we see? You see, guys, the numbers like start 0, 1, 2, 3, 5, 8, and then start going really, really big, right? If I were to look at like A11, this would be what? This would be 89, right? And then if I were to pick A12, now it's already greater than 100. So basically, how can we solve this problem? So one thing you can do is basically you wanna guess what the answer is gonna be like, right? So you can basically, for example, start with if you had a like something like this, well, you could basically decide to plot it. Okay, so if a is equal 0, so if a is equal 0, then the answer is 0, right? But then you can look at, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So you can do 1. You can look at 1, 2. So basically, I'm trying to plot the answer. I'm trying to see, did I notice anything? 5, 6, 7, 8, 9, 10, 11, 12, and it keeps going, right? So this is basically, I plug in, let's say A1, right? A0. So A0 is going to give me 0. But okay, if I plug in A1, what do I get for A1? Well, A1 is going to give me 1. So A1 is going to be 1. Well, what about A2? A2 is also 1. So I also get 1 here. Well, what about A3? A3 is going to be equal to 2, right? So A3 is going to be 2 in here. What about A4? So A4 is going to be 3. So, okay, this is fine. And what about A5? Well, A5 is going to be 5. So it's basically getting bigger and bigger. So you guys see what I'm trying to do here. So it's 1, 2, 3, and then somewhere here is going to be 5. And then what about the next one? Well, the next one is going to be A6 is going to be equal to 8. So if I look at A6, it's going to be equal to 8, right? And then, okay, so A6, actually, maybe I should make it, does look like A7. So this is going to be A6 is going to be equal to 8. And then what about A7? A7 is going to be equal to 13, right? So if I keep going here, A7 is going to be equal to 13, right? So this is the next one. And what about A8? So if I look at like the A8, it's going to be equal to 21. So basically, if I were to expand this, somewhere here is going to be 21, is going to be the next number, right? So you guys see what's happening is that this number started growing really, really, really fast, really quick, right? So it's basically you started, like from here, and then suddenly, these are going to be your answer, right? So it keeps going really, really fast. So there's basically a question here, what is going to be the formula for like AN? Because you see like almost like I'm going to get by A12, this is going to be already like 100. So basically by the time I'm here at, at a big number, right? Like if I look at 12, 13, 14, I'm already going to be in the 100s. So this doesn't even like fit here on the plot. I need to make a smaller plot. So one thing you see that this kind of like grows exponentially. Like here, maybe it's not quite exact, but then from like this part in here, it grows like basically really fast. It just like goes up through the roof, right? So it's a function that grows really fast. So there's actually a reasonable guess you can make in here. So a reasonable guess would be to say that, hey, you know what? Maybe AN is going to be equal to some lambda to the power n. So basically it's exponential. So why does this make sense? Well, it's kind of like similar to, this problem in here, where like at every step, we saw that the answer was doubling, right? So I were to go back to my stuff in here, where when I had like, that AN, so let's say that I had, or maybe I look at the previous problem. So if I look at this problem here, look at every step, it kind of like triples and doubles, right? So basically, if I were to compute what these numbers would be, you see that every step, they kind of like double and triple. So maybe, a reasonable guess would be that AN would be, for example, 3 to the power n. You're going to see that it's not quite 3 to the power n. Well, maybe not quite 2 to the power n, but maybe it's some combination between, maybe it's 3 to the power n plus 2 to the power n with some coefficients, C1 and C2. Maybe something like this, right? Because it's something that's doubling and something that's tripling. So this would also kind of like make sense, right? It's like you take something, you triple it every step, you double it every step. And maybe this one has some coefficient, this one has some coefficient. It doesn't have to be quite like this, but this is kind of like a good guess what the answer could be like. Right. So for now, we don't know what the answer is, but we are trying to figure it out. And we see that, in the previous problem, the numbers are like almost doubling. In here, we see that they're like, for example, tripling and doubling. So maybe if I were to make a guess, what AN is, it would be reasonable to say, hey, maybe AN is going to be some constant to the power n, right? Because this constant, so for example, if you put it 2, it's going to double every step. If you put it 3, it's going to triple. So basically, this constant kind of like tells you how fast the number is growing, right? Like how fast is it tripling? Is it doubling? Is it quadrupling? Is it like multiplied by 10 every single time, right? And then this n is just basically telling you at every step, you just do the same thing, multiply by this lambda. So this is just like a guess. But turns out that this is a really, really good guess. So what would happen if we were to make this guess? Let me show you guys how we can solve this problem. So let's say that I had, so let's go back to, okay, so if I look at, okay, I have this sequence, I have this sequence. Okay, so let's write down this thing. So imagine you have a sequence AN. So let me just create one sequence. So AN is going to be, for example, 2 AN minus 1. Plus AN minus 2. Okay, so I have this sequence that's taking 2 of the last one plus 1 of the second to last one, adding them, and then you're getting the next term in the sequence, right? So, okay, so if I tried to solve this sequence, how could I solve it? Okay, so first of all, well, what is a sequence that satisfies this? So there's like multiple, so like if I have a sequence that satisfies this sequence, it's called a good sequence. So what are some good sequences? Well, it depends on like what conditions you start with. So for example, if I were to start with the sequence, if I were to start with, let's say I start with the sequence 1, let's say I start with the sequence 0, 1. Then what would happen if I start with 0, 1? Well, just plug in 0, plug in 1, you get 2. So the next term here is going to be 2, right? And then what's happening if I plug in 1 and 2. So I plug in the next two terms, 1 and 2. So I get 4, 5. So I'm going to get the next sequence. The next number is 5 here, right? So basically, if I look at like A0, A1, A2, A3, A4, I try to compute them, right? So if I wanted A4, what do? I just plug in 5 and I plug in 2. So I'd get 10, I'd get 12, right? So I'd get 2 times 5 plus 2 is going to be 12. Okay, so I got 12 in here. Okay, so this is also good. So basically, if I look at the sequence 0, 1, 2, 5, 12, this is a sequence that satisfies this relationship, right? So now if I can keep going, maybe, A5, what's going to be A5? Well, if you look at A5, plug in 12, plug in 5, so you're going to get 24 plus 5, 29, right? So you're going to get that the next number is 29. Okay, so you basically have this thing in here that is a good sequence. Okay, but what does the sequence depend on? Well, the sequence depends on the only two terms, right? If I give you some starting conditions, A0 and A1, you know what the first two terms are, then this defines the entire sequence, right? There's like no place for like changing what AN is, because AN depends on the last two terms, and every term depends on like the previous two terms. So basically, whatever the first two terms are, they get the sequence started, right? So these are kind of like the initiating ones. If, for example, I had like plus 3 AN minus 3, for example, if the sequence was like this, that it looked back 3 terms, right? Then this would be, I would need like the first 3, right? So we'll take a look. We'll see what's happening when I have 3 terms as well. But basically, this is kind of like the idea is that like if you have the last 3 terms, then it would depend like on the first 3 terms in the sequence, right? But okay, for now, let's just focus on like 2 terms. Okay, so this is called a good sequence. Good sequence. Because it satisfies this relationship in here, right? But now here is the thing: is like if you have there's not only one good sequence, there's multiple good sequences. It all depends on the starting conditions. So let's like take another look. So what if I had a sequence that started with 3 and 2? What would happen with this sequence if I start with 3 and 2? Well, if I plug in 3 and I plug in 2, what do I get? So 3 plus 4, I get 7, right? So the next term would be 7. Okay, so I got the next term is 7. Okay, but now what's happening next? So if I plug in, 7 and 2 for the last two terms, I get 14 plus 2, I get 16. Okay, so the next term is going to be 16 in here, right? And now I plug in again 16 and 7. What do I get? So I guess 32 plus 7 is going to be 39. Okay, so I got another term, 39, right? And then, okay, what is the other thing I can do? Well, if I plug in, 39 and 16, so if I plug in 39 and 16, I get, this is going to be 40 times 280, so 78. 78 plus 88, 94, right? So I just get 94. Do you guys agree with that? So I get like 94, right? So basically, if I started with this two, so same thing here. If I start with this two, then I can get the entire sequence, right? I can get the entire sequence. Now, here's the deal. So this one is also a good sequence. So let me write it. This is also good. Also, maybe I'll write also on top of also. Good sequence, right? Now, here is the deal. If you have, but this sequence starts with 0, 1, this sequence starts with 3, 2. But the thing is, if you have two good sequences, you can always combine them. So here is the thing. So if I have a good sequence and another good sequence, what's happening at the sequence that I take their sum? So for example, if I were to take their sums, this would be the sequence 3, it'd be 9. So what I do is I sum them, and then 16 plus 5, 21. And then, 12 plus 39, this would be 51. Sorry, did I get it right there? 21, 51. 51, and then I keep going. 94 plus 29, this would be 23, 123, right? Then what ends up happening is that if I sum two good sequences, this is also going to be good. Well, let's check that this is true. So if I were to plug in 3 and 3, what would I get? So 3 plus 6 is equal to 9, so I get the next term 9, right? Okay, so the next term 9 is fine. Now, if I plug in 3 and 9 in here, so what do I get? 18 plus 3 is going to be 21, right? So I get 21, which is exactly the next term in the sequence. So you guys see, if I combine two good sequences, I get another good sequence. Okay, so now what about next thing? So the next thing is maybe, I got 21. So maybe I plug in 21 and 9. So I plug in 21. Sorry, 21 is the last term. So 21 and 9. So, okay, so this is going to be 42 plus 9 is going to be 51. So if you combine this, you're going to get 51. So you see, this relationship basically keeps working. So if you had two good sequences, you can sum them and you also get a good sequence. In fact, you can also take their difference. If I were to look at their difference, what would be their difference? So if I were to look at their difference, 3 minus 0 would just be, 3. And then 2 minus 1 would be just 1. And then 7 minus 2 would be 5. And then 16 minus 5 would be 11. And then 39 minus 12 would be, I don't know, like what, 27, right? And then, if I were to do 94 minus 29, so it would be 63, right? So you guys see, I get this sequence here is also good. also is going to be a good sequence. So if I take their difference, this is also a good sequence. Why is that the case? Well, the way you can see this is basically this. If you had a sequence AN, so maybe, I don't know, maybe this thing in here, this is our sequence AN. Well, and maybe, so basically, maybe this is our sequence AN, and now let this be our sequence BN. So because this is a good sequence BN, it satisfies the same relationship. So BN satisfies the same relationship. There's going to be 2BN minus 1 plus BN minus 2. Now, here is the thing. What is happening if I were to create a new sequence, let's say the sequence CN, which is going to be AN plus BN. Well, then look at this. If I were to sum this two, what would I get? Well, I need to sum this two and I need to sum this two. So basically what I'm trying to say is if I were to do AN plus BN, right, this would be 2 AN minus 1 plus BN minus 1 plus, AN minus 2 plus BN minus 2. So basically, if you take two good sequences and if you were to sum them, you'd get another sequence CN. So basically, now you can plug in the number. So AN plus BN, this is just going to be CN, is going to be equal to 2 times CN minus 1 plus CN minus 2, right? Do you guys see this? So the two of this is going to be this term, and the two of this is going to be this term. So basically what I'm trying to say is that, hey, if you've got two good sequences, if they both satisfy the same relationship, the two of the previous one plus the second to last one, right? Then this is the same. If both of them satisfy their same relationship because they're linear. So this is the whole idea, is because these sequences are linear. So as long as this is linear and this is linear and they have the same coefficients, when I add them, the coefficients are going to be the same. So they can come in front of the parentheses. So you just add them, AN and BN. This is basically AN minus 1, BN minus 1. This is kind of like adding just two sequences, right? And then I add this two and I get, this is a new sequence CN that has this definition. So this is going to be CN minus 1, CN minus 2, right? You can define another sequence, for example, where you take the difference. So if I were to define CN to be not the sum, but to be the difference, well, then what I can do is I can take minus here, and I can take minus here. So this would be a minus, this would be a minus, and this would be a minus. But see, the thing is, you still get this is going to be CN, it's just going to be the difference. Now CN minus 1 is going to be the difference, CN minus 2 is going to be the difference. So the whole point is that, hey, if you have two good sequences, you can add them or you can construct them, and they're also going to be good sequences. In fact, you can do more than that. You can, for example, take 2 times this sequence plus 1 times this sequence. So basically, you don't need to take them in the ratio of like AN to BN. For example, you can take 3 of this sequence and 7 of this sequence. And what is happening if I were to do that? Well, if I were to take, if I take 3 of this sequence, then I can just multiply this by 3, multiply this by 3, multiply this by 3. So I multiply this by 3 everywhere. And then I multiply the second one by 7. So if I multiply this sequence by 7, 7, 7. But actually, here's another thing. If I have a sequence, if AN is a good sequence, so let's look at this. So before I do that, let's say that I have AN is a good sequence. So AN is a good sequence, right? Then what is happening if I create a new sequence CN that's going to be, let's say, 7AN? So if I take a good sequence and I multiply everything by 7, right? It's also going to be a good sequence because look, if I were to multiply this by 7, multiply this by 7, and multiply this by 7, then what would I get? Well, this would just be basically CN is going to be equal to 2 CN minus 1 plus CN minus 2, right? You guys see that, AN multiplied by 7 is going to be CN. So basically, this thing is here, this thing is here, this thing is here. So what I'm trying to say is that if you were to take a good sequence, AN, and it's multiplied by a constant, double it, triple it, multiply it by 10, and you were to plug this sequence in here, it would also be a good sequence. So CN would satisfy the same relationship. It has coefficients 1 here, 2 here, and then 1 here, right? So like the next term is the double the last one plus the penultimate one, right? Like plus, but the second to last one, right? So basically, you can also multiply by 7. So this is going to be a good sequence. So now basically what I can do is I can stay instead of like doing this, instead of combining CN, maybe I can look at, so let's say CN is going to be 7 AN minus 1, right? So if I let's say that this is going to be equal to this. So basically what I'm trying to say is that, if I define CN to be this, then look at 7 AN is also going to be a good sequence. And I can just like write it here, write it here. And maybe I can take 3 of this one. Well, 3BN is also going to be a good sequence, right? BN is a good, so 3BN is also a good sequence. So, 3BN minus 1, minus 2. These are also going to be good sequences. But well, what's happening when I combine them? Well, I'm going to get 7 of this and 3 of this. So 7 of this and then 3 of this, and then 7 of this and then 3 of this, right? So now what do you see? Well, you see that if you combine, 7 of this sequence plus 3 of this sequence, what do you get? You get CN, right? So 7 of this plus 3 of this gives me CN. 7 of N minus 1, 3 of BN minus 1 gives me CN minus 1, right? And then again, 7 of AN minus 2, 3 of BN minus 2 gives me CN minus 2. Right, so sorry, this 7 thing in here should be inside the parentheses. So this 7 is inside the parentheses here. Okay. Okay, so hopefully this whole idea is clear in here. What we are doing is basically, if you have a linear sequence, you can take linear combinations of it, right? So in fact, I could have, instead of taking 7 and 3, I could take any coefficients, right? I could have taken any coefficients. So for example, if I take, instead of picking 7 and 3, I could have taken any coefficients, P and Q. So for example, if I were to make this a P and then this a Q, this would also be like a good sequence. So in some sense, if I have good sequences, I can combine them, right? Okay, but what is going to be the most correct good sequence? Well, it depends on the starting conditions. If I were to give you this thing here, what I usually should give you is I need to give you the starting conditions, right? So I basically need to tell you that, hey, you know what, maybe A0 is equal to 5 and maybe A1 is equal to 7, right? So I have the starting conditions. Okay, so what can you do with the starting conditions? Well, one thing you can do with the starting conditions, you can look at, okay, what sequence, from all the good sequences, you can look at all the good sequences. There's an infinite number of them, right? Any linear combination of them. There's an infinite number of good sequences. Which one starts with 5 and 7? And well, you're like, okay, does any start with 5 and 7? Not any that I see here. So basically what you need to do is, you need to think about, okay, how can I take linear combinations of this, like, maybe this good sequence and this good sequence, such that they start with a 5 and 7. So if I got some linear combination that contains 5 and 7 as the start one, then that's going to be the good sequence that we're looking for, right? It's the good sequence that also satisfies the starting condition. So a good sequence is the one that satisfies the relationship here, the recurrence relationship. But the proper good sequence is the one that also satisfies the starting conditions, that it needs to start with a 5 and a 7, because there's an infinite number of them that satisfy that, right? Okay, so now that we have an idea of like how we can combine good sequences, so if they're linear, we can take linear combinations, right? I can take 3 of this and 7 of this, or like 10 of this and minus 2 of this, or any other variation. Well, then now we can basically go a little bit back to our problem. We're looking at Fibonacci numbers. So again, we're trying to figure out what is going to be the good sequence that satisfies the starting conditions. And we kind of like saw 2 ideas. One is that we can combine good sequences. If I had some good sequence and another one, I can combine them. But it's a bit unclear. How should I combine, 5 and 7? It's tricky, right? But then another thing you could do is, well, this thing that we say that, AN grows very fast, grows kind of like an exponential. So a good guess for it would be that, like AN is going to be equal to some lambda to the power n, right? Okay, so let's maybe, take a break from the previous idea. It's going to be important in a little bit, but now let's just mainly focus on, this idea in here that AN is going to be lambda to some power n. Okay, so what would happen if I were to take this solution and maybe, plug it in here? So I guess you see this grows like very fast, grows very exponentially. So let's maybe, look at the previous problem. This one, AN is equal to like 2 of this. So let's maybe look at, let's maybe do this thing here. So AN is going to be equal to, so let's do it this way. So AN is equal to 2 AN minus 1 plus 3 AN minus 2. So maybe I have like something. Let me see if this makes actually sense. So, okay, so let's call this, let's change the coefficients a little bit. So let's say this is going to be 4 AN minus 1 plus, yeah, 4 AN minus 1 minus 3 AN minus 2. So basically what I'm doing is I'm defining a new sequence AN, which is going to be 4 times the previous term in the sequence minus 3 times the other one, right? So it doesn't always have to be with a plus, right? It can also be a minus. So now basically what I'm going to try to do is I'm going to try to solve the sequence. So let's maybe, start with some starting conditions. So let's say that A0 is equal to 1. And let's say that maybe A1 is equal to 3. So, okay, so I got the starting conditions here. So I'm going to write here as C is the starting conditions, right? Okay, so now I'm trying to solve this sequence. Okay, so what do we have in here? Okay, so I guess let's write it down. So if I were to compute a couple terms, we remember what we say. We have to make a guess. So we basically guess. So we want to guess that AN. So the term AN is equal to lambda to the power n, right? So this is basically the guess that we want to make. Okay, so what is happening if I were to put this guess here, and this guess? So, what I'm trying to say is that, I'm going to take this guess and I'm going to plug it here, and in here. So what would happen if I were to, like take this guess and like plug it in all 3 of them? Well, then what I get is going to be a quadratic equation. So if AN were to actually be this sequence, right? Then what would be, what does lambda have to be to satisfy this relationship? And you see that it's going to be lambda to the n is going to be equal to 4 lambda n minus 1 minus 3 lambda n minus 2, right? So one thing you can notice right away is that, because this is exponential, you can simplify lambda to the n minus 2, right? So if I were to simplify this would just be, like you can simplify this to a quadratic, right? So you can rewrite this as what? You can rewrite this as like, lambda squared is equal to 4 lambda minus 3, right? You guys see that? Because, I can simplify all the lambda. So this is really nice. This is why I want to use lambda to the n, because, I can simplify it very nicely. So if I do this simplification, so basically I write it like this. So this is what? This is a quadratic equation, right? Let me rewrite this as a quadratic equation. I can rewrite this as like minus 4 lambda plus 3 equals 0. So now this thing in here, this is called the characteristic equation. This is the characteristic equation of this sequence. So, right. Heuristic equation of the sequence. Okay, so now what can I do? Well, I need to figure out what lambda is. So I need to solve this, right? So how do I solve it? Well, there's the standard precision, right? You can figure out what delta is. So delta is going to be equal to minus b. So it's going to be equal to, 4. So delta is going to be b squared minus 4ac. So b squared is going to be 16 minus 4ac. So 4ac would be, minus 12, right? So 12. So this would just be equal to 4. So if I wanted to compute lambda 1, 2, this would be equal to what? Minus b. So it'd be 4 plus or minus square root of 4 divided by 2, right? So what do I get? So I'm going to get 6 and 2 divided by 2. So there's like 2 solutions here, right? So let's see, b squared minus 4. So let me see if I got anything wrong. So I get the solutions. Yeah, I got basically, I get 2 solutions, right? So what's going to be the solution? So you see the solution is going to be 3 and 1, right? So there's going to be, 2 solutions for it. So there's going to be, a lambda that can be either, lambda can be either 3 or lambda can be equal to 1. Okay, so now basically an has 2 possibilities. So if I take, if I were to take an, so an can be basically, can be equal either 3 to the power n, or it can be either equal to 1 to the power n. So actually, if I were to plug in 1 to the power n, what would I get? This would be 1, 1, 1. See, this satisfies. 1 is equal to 4 times 1 minus 3 times 1. So it's basically 1 is equal to 1. This works. But then if I were to plug in 3, and then I were to plug in, so 3 to the power n, right? So if I were to plug in 3 to the power n, this would be like, for example, 3 squared. This would be 3, and this would just be 1, right? So like 3 to the power 1 and 3 to the power 0. And if I were to plug in the numbers, I'd get 9 is equal to 12 minus 3, right? Because this is just 1. So 12 minus 3 is 9. So this works. So basically, this sequence is going to be a good sequence. And this sequence is going to be a good sequence. So basically, if I were to look at the sequence, that's 1, 1, 1, 1, 1, 1, 1, it's a good sequence. And if I were to look at the sequence that's made out from the powers of n, so the sequence that's made out from the powers of n is going to be 1, 3, 9, 27, 81, this is also a good sequence, right? So basically, I got kind of like 2 fundamental sequences. There's like lambda 1 and lambda 2. So they gave me 2 fundamental sequences. There's this sequence and this sequence. Well, but now what can I do? Well, if this is a good sequence, I can take any linear, I can double it, I can triple it, I can multiply it by 4, 5, 100, divided by 1/2. So if I take any coefficient, if I take any coefficient C1 in front of the sequence, this would also just be a good sequence. It's just everything is going to be multiplied by C1, right? But this is also going to be a good sequence. So basically, you can take a good sequence and you can multiply it by any constant. So in this case, for example, if I were to multiply it by C1, by constant C1. Now you can take this sequence and you can also multiply it by another constant C2. This is also going to be a good sequence. And now what you can do is basically you can take linear combinations. What I'm trying to say is that if an has 2 options, that it can be either this or this, then what you can say is, you can say that, more generally, an can be any linear combination of the 2 sequences. So you can say that, in this case, an can be basically, some coefficient C1, 3 to the power n, plus some coefficient C2, 1 to the power n. So basically, an has, 2 possibilities. More generally, how would we do like, this lambda 1 and lambda 2 was 3 and 1, but maybe, I had different coefficients. So if the coefficients more generally were like any like lambda 1 and lambda 2. So basically, if an had, the option that it could be lambda 1 to the power n, and if it had the option that it could be lambda 2 to the power n, then what would be the good sequence? Well, the good sequence would be 1, lambda squared, lambda cubed, lambda to the 4th, right? So it's lambda 1, right? Right, but then there would also be another good sequence, 1, lambda 2, so basically lambda squared, lambda cubed, lambda 4, lambda 4, but this would be lambda 2, right? Lambda 2, lambda 2, lambda. So basically, I got a good sequence and I got another good sequence, but then I can also take linear combinations, C1 and C2. So more generally, this is the special case, 3 and 1, because these were the roots. But more generally, the solution would be like this. AN would be, C1 lambda 1 to the power n plus C2 lambda 2 to the power n. So this would basically be the solution. Does this make sense in here, guys? So basically, what you want to do is, if you want to solve the system, what you do is you do the guess, right? So the guess is like right in here. So you want to do this guess, you take this guess and you plug it in here and you get a quadratic equation. So you basically get from here, you get a quadratic equation that is going to give you two roots, lambda 1, and lambda 2, two roots, lambda 1 and lambda 2. And then what you do is you take these two roots and then you put them in here and in here, right? So then your solution is going to look like this. Now you might say, okay, but what is the final solution? Because, okay, lambda 1 and lambda 2 I computed. So I get this equation here, right? But there's still two things that are missing. There's C1 and C2. So, the question is, what the heck is C1 and C2? So it's basically, we're getting to the original question. I have found a good sequence, the powers of 1, and then I found a good sequence, the powers of 3. So it's kind of like, saying that, okay, I have a good sequence and another good sequence. But, well, what are all the good sequences I can get? Well, you can take any linear combinations, right? So the question is, how do you combine the sequence? Maybe I'm going to use some C1 of this one and then some C2 of this sequence. What coefficient should I use for C1 and C2? How should I combine these two sequences such that I'm going to get a good sequence that satisfies, that's going to satisfy the starting condition? So we kind of like get the same question here, right? It's like, I have this good sequence, but what is the starting conditions? Well, these are the starting conditions, right? So you should take the starting conditions, plug them in here, and you should, from here, you can basically compute, okay, what are going to be, the coefficient C1 and C2. So let me clear this up a little bit. So, I guess what is one thing that we can do? So you take the starting conditions. So let's take a look at the starting conditions. So what is going on with the starting conditions? Well, you plug in the values n equals 0 and n equals 1. So what you want to do is, if you plug in n equals 0, so if you plug in n equals 0, what would we get? So if n equals 0, you just get n equals 0 is nice because you get a0, right? So you get that a0 is going to be equal to 1. So if you plug, so this is how you do it. So you take here, you plug in n equals 0 here. So you're going to get a0 is going to be equal to 0, 0, right? So this is just going to be a 1, and this is going to be a 1. You can forget them. So basically, a0 is going to be C1 plus C2. Well, but a0 is equal to 1. So you just write this is 1, right? So whenever you plug in a0 and 0, you just get C1. So basically, but like more generally, if you plug in, n equals 0, you plug it in here. What would you get? This would be a 0. This would be a 0. So they just become a 1. So you forget about this. So you just get that a0 is always C1 plus C2. So basically, you look at, C1 plus C2 is always going to be the first term in the sequence. So I guess, I can just like write down, how would I solve it? I just look at the starting conditions, right? So I just say that, a0 is going to be equal to C1 plus C2 is always, and is equal to 1. Okay, now what about a1? Well, just plug in, 1 in here, and you plug in 1 in here and 1 in here. So basically, if I were to plug in n equals 1, I plug 1 here, 1 here, 1 here. What do I get? I get that a1 is going to be equal to what? C1 lambda 1 plus C2 lambda 2, right? So if I want a1, it's going to be C1 lambda 1, C2 lambda 2. So basically, a1 is going to be equal to C1 lambda 1 plus C2 lambda 2. And this is equal to what? This is equal to 3 in our case, right? So basically, what you want to do is you want to solve this system of equations. Okay, lambda 1 and lambda 2, you already know they're going to be 3 and 1. So I can just, remove, instead of like writing this like this, I can write, 3 and 1 here if you want, if you wish. So 3 of this and 1 of this. Okay, so I got this. C1 plus C2 is 1, and then 3C1 plus C2 is going to be equal to 3, right? So you can, this is a system of two equations. It can be solved very easily, right? You can, how would you do it? Well, you can do, for example, if you do their difference, you do this minus this, you're going to get C2 is going to cancel, right? So then you're going to get C1, so you're going to get 2C1 is equal to 2. So basically, so let me keep in the values. So basically, it's going to be 3 of this and then 1 of this. So if I were to solve the system, I would get what? I would get that from here, I would get that, C1 is equal to 1, and then C2 is going to need to be equal to 0. Right, does this make sense, guys? Oh yeah, it does actually make sense, right? Because, I started with the coefficients 1, 3. Oh, look, so actually here I got really lucky. I got really lucky because I said I started with coefficients 1, 3, so it was exactly the sequence, right? So we got 1 and 0. But let's say that I had the starting conditions weren't 1 and 3. So what if the starting conditions were, I don't know, let's say 2 and 3, right? So if the starting conditions were 2 and 3, what would happen? Well, this is good sequence. So this would need to be a 2. So this would be a 2 here, right? So, okay, so what would be C1 and C2 in this case? So maybe if I simplify this, right? So Yes. So basically I'm saying, what if that one was a 2, right? So then this one is going to be a 2. So what would I have? So I would have that, if I were to do their difference. So if I were to simplify, so I'd do this minus this, b3 minus 2 is 1. So this will just be 2c1, so divide by 2. So I get c1 is going to be basically 1/2. And then what about c2? Well, I get c2 is also going to be equal to 1/2, right? Sorry, no, c2 is going to be equal to 3/2 because they need to sum up to 2, right? Okay, so basically this is it. So now you're going to answer. Your answer is going to be, in here, your answer is going to be, it's going to be 1/2, 3 to the power n plus 3/2 times 1 to the power n, right? So that's basically, this is going to be your sequence an. So if you take this sequence and you plug it in here, you're going to get the coefficients 2, and then you're going to get the terms. The first term, when you plug in n equals 0, when n equals 0, you sum the coefficients, right? You get 2. When you plug in n equals 1, you sum them and you get 3. And then you can keep going, right? So now if I come to you and I ask you, hey, I have this sequence with this is the starting conditions, and then I ask you, what is going to be a 100? Well, what you can do is you can just take this, plug it in here. So you plug 100 here and you plug 100 here, and then, okay, that's it. If you plug 100 and 100, you put them together, this is going to be your term a100, right? Does this make sense, guys? So basically, if you wanted to get, what a100 is, what you can do is you can, just, this is your final formula. So you plug in, a100 here, and then you got your answer. Okay, so this is kind of like really, really, really good stuff. Okay, 1 to the power n. So okay, so we got, and then more general, the sequence looks like this, right? So we kind of like already established that there's, there's 2. So see, this is kind of like the idea in here. There's 2 degrees of freedom. So how do we understand degrees of freedom? So the way to think about the degrees of freedom, there's like 2 things that you can vary. So if you look at, this is your sequence, right? It's gonna have, when you plug in lambda equals n, because there's 2 terms in here, there's gonna be a quadratic equation. So there's gonna be 2 terms, like lambda 1 and lambda 2. So the lambda 1 and lambda 2, you need to combine. So lambda 1 and lambda 2 are fixed, right? They depend on the coefficients 4 and 3. So lambda 1 and lambda 2 are going to be fixed in here. But then the things that you can vary, the degrees of freedom, are the coefficients. It's like, what coefficients should I pick? How much of the first sequence? How much of the second sequence, right? How much of this sequence should I take? And how much of this sequence should I take? And how should I combine them? So the 2 degrees of freedom, they depend on the 2 coefficients, right? Because the starting conditions have 2 options. Like the starting conditions, there is two things that you can vary: the first term and the second term. So depending on how you vary the first and the second term, you can get like, an infinite number of, good sequences that satisfy this like starting condition. So there's an infinite number of starting conditions and you can get an infinite number of good sequences, right? So, but the starting conditions, they depend on like 2 variables. They have 2 degrees of freedom. So because of that, there is 2 coefficients that you can adjust here. And this is always going to be the case. If the starting conditions depend on the first 3 terms, for example, there would be 3 coefficients that you can adjust in here. Okay, so any questions about this? Yes? No? Okay, so I guess this is, this is how you think about linear recurrences when you have just like 2 degrees of freedom. But now I guess the next question is, what is happening if we try to look at like some more advanced problems? So actually, okay, maybe before we do that, maybe it's worth it to do an exercise and, just to get a little bit more practice with this. So we kind of like did this exercise in here. So maybe, we can do another exercise. This one's going to be a little bit harder, problem 10.2. But before we do that, let's look at like this thing. So first problem, we already discussed it and we did it right. We saw that, there's a relationship in here. And the relationship was what? That if you want to move 8 rings, it's 2 times the previous one plus 1, right? So we got this relationship that an is 2 times an minus 1 plus 1. And we saw that's all these numbers. And you notice that if you add plus 1, it's all powers of 2, right? So that's the observation. Okay, so now here's another problem. So let's look at this problem. So what is this problem? So problem 10.2. What does problem 10.2 say? So if I scroll a bit down, so let's look at this one here, right? So what is happening? So I work for a valid parking company, right? So what do we have? So each of our customer drives either a Cadillac, a Continental, or a Porsche, right? So there's 3 types of cars. There is a Cadillac, let's call it D. There is a Porsche, let's call it P. And there's a Continental, let's call it T. And now my boss have told me to reserve spaces in our parking lot and mark them as being Cadillac, Continental, or Porsche. So basically, let's imagine your parking lot is going to be something like this. So, maybe, I don't know, maybe you have, so you have, for example, like, this is going to be your parking lot. So you have how many spots in here? You have 1, 2, 3, 4, 5, 6, 7. So you have 7 spots in here, right? And now what does the problem say? So the problem says that basically Cadillacs and Continentals take 2 spaces, right? So if I wanted to park a Cadillac would need to take two spaces. It would be like this, DD, like a Cadillac. If I wanted to park a Continental also takes 2 spaces. They're big cars. But if I want to park a Porsche only requires 1. So for example, I can make this a Porsche spot, I can make this a Porsche spot, and I can make this a Porsche spot. right? So basically, if I wanted to park, for example, there's an option to park one Cadillac, one Continental, and 3 Porsches if I were to like do this marking, right? So now the problem is saying is that basically you take care of the customers. So the boss told you to reserve the spaces in the parking lot. So what you need to do is you need to allocate the spaces. You need to decide, okay, what's going to be a Porsche, what's going to be a Cadillac, what's going to be a Continental. So the question is, in how many ways can I, color the spots? So basically, for example, I can say that, this is going to be a Cadillac D, and then I can call this to be a D. So this is like, and then I can call this to be a T. And then I can call this to be a Porsche, right? So then the question is, in how many ways can I assign these seats? Cadillac, Porsche, Continental, right? In how many ways? Like how many ways can I, color the floor, like mark the spot? So basically, make this to be Cadillac, this to be Cadillac, this to be Continental, this one to be a Porsche. So I come and I write down. So basically, I make this one spot. This is going to be one spot. This is going to be one spot, and then, so basically, I do separations, right? So I can write a bar here, a bar here, a bar here, and then I'm going to say this is going to be the Cadillac spot. This is going to be the Cadillac spot. This is going to be the Continental one. This is going to be the Porsche one. So in how many ways can I do the splitting? So remember, if you look at the Cadillacs, they take 2 spots. Continentals take 2 spots, but the Porsche takes only 1 spot, right? So see, this seems like kind of like a hard problem. There's like a lot of like casework here. So one thing that you could do is like, okay, let's say that if I had n spots, so if, in here I have, n spots. So this is 7 spots, right? So maybe the answer here is going to be A7 if you have 7 spots. But if you were to have, let's say that I had n spots, then let the answer be AN, right? So if I have n spots, the answer is going to be AN. So then the question is, how many, what's going to be the answer like more generally, if I change from like n to like any other arbitrary number. So okay, so now I guess you can maybe it's worth it to make a new screening here. So let's look at this problem with Cadillacs, Porsches, and Continentals, right? So okay, so Cadillacs are gonna take 2 spots. So if I were to look at like this this one is a Cadillac, right? So okay, we have the option for the Cadillac, and then we have the option for the Continental. That's gonna be TT. So the Continental takes 2 spots, and then we have the option for the Porsche. The Porsche takes just 1 spot, right? Okay, so let's look at, for example, like let's say that, n spots gives me the answer, AN. So now let's just kind of like start with, let's say that I had just 1 spot, right? Well, what is the option? What can I make this spot? Well, clearly Cadillac doesn't fit, the Continental doesn't fit. So the only option is that you can make this to be a Porsche, right? So I can make this thing to be a Porsche. So I can just say that, like A1 is going to be equal to 1 because it has only 1 option, right? Okay, so now let's look at the next thing. What is the next thing you can do? If you were to have 2 spots, right? If I have 2 spots, well, how many options do I have in 2 spots? Well, now there is actually options. I can make this to be a Cadillac. I can make this to be a Continental. And I can also make this one to be a Porsche, right? So if I make this one a Porsche, this one's a Porsche. So you see that there is like 3 options, right? Options. So there's like the DD and there's also the TT. So there's like 3 options. So basically, A2 is going to be equal to 3. So if you have 2 spots, there's like 3 ways you can like split Cadillacs, Porsche, and the Continentals, right? So you guys see the problem gets very interesting very quickly. So now, what if I had 3 spots? What if I wanted to compute this term, like A3? What is going to be A3? Well, you think about A3, think about it this way. You have 3 spots now, right? 1, 2, 3. Okay, so now what are the options? Well, I guess you can kind of like start with the first one or the last one. You can ask, okay, what is going to be the first one? Well, is the first one going to be, well, the first one can be a Cadillac. So if it's a Cadillac, then it's going to be D, and then the last one is to be a Porsche. Well, the first one can also be a Continental, right? If it's a Continental, you're going to have TT, and the last one is to be a Porsche. But also the first one can be a Porsche. Okay, but what's happening if the first one is a Porsche? Well, there's actually 3 options, 1, 2, 3, right? Because now you have 2 more spots you need to decide. So you have 2 more spots you need to decide. Well, so what can these 2 spots be? It can be a Cadillac, or they can either be a Continental, or they can also be a Porsche and a Porsche, right? So this is a Porsche and this is a Porsche. So you see you have 3 options here and then plus 2 options. So in total, you're going to have 5 options. Does this make sense, guys? So basically there is, if I had only 3 spots would just give me 5 options, right? Okay, so this is kind of like interesting. So it seems like the numbers are going to grow really fast, like 1, 3, 5. And it seems like, if I wanted to solve the problem for like 3 of them, I need to know what the problem is with 2 of them. So you see, guys, the problem with 2, it's actually here. It's like, how many ways can I assign 2 spots in them? And there's like, 3 different options. So the way you can think about a problem more generally, let's say that, I had n spots in general, right? So what would I have for n spots? So let's write down, this is going to be 5. So how would the problem go for like n spots? Well, for n spots, you'd have, something like very, very long. So let's say this is going to be n spots, right? And then, well, the answer in here is going to be an, right? So now the thing is, I'm trying to figure out what is an. Well, there's a couple of things I can condition on, right? So I can basically look at, like, for example, the last one. What is going to be the last car? Well, the last car has an option. The last car can either be a Porsche, right? So if the last car is a Porsche, how many options do I have for the remaining problem? Well, there's going to be n minus one spots. So the answer is going to be, there's going to be n minus one options, right? If the last one's a Porsche. So if the last one is a Porsche, there is, an minus one options. But okay, what if the last one is a Cadillac? Well, if the last one is a Cadillac, right? If I make this a D and a D, it needs to take 2 spots. So in here, I'm gonna have n minus 2 spots, right? Left. So if there's n minus 2 spots, the answer is gonna be an minus 2, right? There's an minus 2 to if the last one's a Cadillac, there's an minus 2 to fill out the rest. If the last one was a Continental, again, there would be, an minus 2 to fill the rest. And then if the last one was a Porsche, then there would be, basically an minus 1 to fill the rest, right? So you guys see what I'm trying to do? So basically, if the last one is a Cadillac or a Continental, there is an minus 2 options. But if it was a Porsche, it's an minus 1. So we get the relationship. We get the relationship that, if you wanted to compute an, it depends. If the last one's a Porsche, it's going to be an minus 1 options. And if the last one's a Cadillac or a Continental, it's going to be an minus 2 plus an minus 2. Right? So because, so the answer is going to be 2 to an minus 2. Now let's say that we also had, we had a third, so this is the case where I have Cadillacs, Continentals, and Porsches. But maybe what if I come and I adjust the problem, and let's say that I also have a really, really big car, maybe, I don't know, maybe I have a Jeep or I have maybe a Tesla Cybertruck, right? So the Cybertruck is gonna, take 3 spots, right? So Cybertruck is going to take C. So basically it's like 3 spots, right? So then you could ask, okay, if I were to have a Tesla Cybertruck was the last one, then there's basically going to be an minus 3 options, right? So you also have this option, an minus 3. So basically, you see, depending on the problem, is that there can be multiple terms, not necessarily only stop at 2. It can also go down to 3 or more, right? Depending on the problem. It's just the thing is that there's a lot of casework, and the problem with an is actually can be solved by looking at the sub problems, the smaller problems, the previous case, right? So if you wanted to solve it, if you had 100 spots, if you knew the answer for 99, 98, and 97, you can combine them to get the answer, right? Well, but for now, I guess let's not make the problem too complicated. So let's get rid of the Cybertrucks. We cannot park Cybertrucks here yet, for example. So, we cannot have 3 spots. So we can only have, this 2 cars in here. Okay, so we would get, a sequence like this. And then again, you would want to solve the sequence, right? So how would you solve the sequence? Well, there's, 2 options here. There's going to be, well, I guess, I make the guess, an is equal to lambda to the power n. And then what would I get? I would get, lambda to the n minus 1 plus 2 lambda to the n minus 2 is equal to lambda to the n, right? Is equal. So then this is going to be a quadratic, right? So if you want to write this as a quadratic, you're going to write lambda squared is going to be equal to lambda plus 2. And then what can you do in here? You can solve it, right? So I guess you can write it like lambda squared minus lambda minus 2 equals 0. So you can solve this thing. So if I were to solve this, delta would be what? Delta would be b squared minus 4ac. So delta would be equal to 1, delta would be equal to 5, right? Do you guys agree with that? Minus 4ac, no. Sorry, delta would be 9, right? Because it would be 4ac, it would be 4 times 8, minus, so b squared minus 4. So it'd be, delta would be 9. Okay, so what would be lambda 1, lambda 2? So I guess lambda 1, 2 would be equal to, I guess, minus b, so it'd be 1 plus or minus square root of 9 divided by 2. So what are the options? Well, it's going to be 1 plus or minus 3. So 1 plus 6 is going to be a 2. And then 1 minus 3 and minus 1, right? Do you guys hear this? So basically, this would be the 2 solutions, lambda 1 and lambda 2. And then you would get what? You'd get that, you try to solve the system. So you'd say that, basically an, you just write it, an is equal to, basically C1 3 to the n plus C2 minus 1 to the power n. So it's basically lambda 1 and then this is lambda 2, right? Okay, and now you want to solve this. So how can you solve this? Well, you need to plug in the numbers. So what do you have? You have A1 and A2. So you basically say that A1 is going to be, C1 3 plus C2 minus 1. And then if you want to get A2, and you know that it's going to be equal to 1. So you say this is equal to 1. And then what about A2? A2 is equal to 3, but it's going to be, C1 times 3 squared. 3 squared plus C2 times, minus 1 squared. So you get this is equal to 3, right? Okay, so this is nice. This is nice. So you guys see one thing in here is that we're missing A0. So I don't have any A0. So this is really, really sad because, if I had A0, Okay, so I can solve the system, but if I had a0, it's like much easier to solve the system, right? Like, look at this, if I were to plug in n equals 0, if I knew what a0 is, if I were to plug in 0, 0, 0, I just get, c1 plus c2 is equal to a0. This is really nice. And then if I were to plug in n equals 1, I'd get, c1 lambda 1 plus c2 lambda 2 is equal to a1. So it would be really nice to have a0 and a1 instead, right? Because if I didn't have a0, then I would need to use a2. So I'd write, a2 is equal to c1 lambda 1 squared plus c2 lambda 2 squared. Okay, this lambda 1 and lambda 2 are easy, but imagine your lambda was, 1 plus square root of 3 divided by 2, something like this, right? Then if I wanted lambda squared, this would be squared. See, it would get very complicated very easily. So the thing is, it's much nicer to, use lambda to the 1 and be this, but it's much nicer to use lambda 0 because lambda 0 just use this to the power 0. So for example, this would be really nice, right? Because, I can just forget about this. This is just 1, right? So I just get this nice equation. See, whenever you have a 0, it's just always just c1 plus c2. So I would really, want to be able to use, lambda equals, sorry, not lambda, but like n equals 0, but I do not have n equals 0. So because I do not have n equals 0, I need to look at this equation with a2. So I need to use, basically what equation? So I want to use, equation 0 and 1. But I cannot use 0 and 1. So instead of this, I need to use 1 and 2. So then the question is, how can I get, the equation with a0? And turns out there is an option. So basically, let's say that I had this system of equations. So what is the relationship? So I guess let's rewrite this again. So let's look at these two things. So I have the starting conditions here, and I have the sequence here, right? So what can I do with this sequence? Well, guys, look at this. I can do the sequence backwards. So basically, for example, I wanted to compute. So I can go with the sequence forward. So for example, if I were to plug in 1 and 2, then I'll get the sequence for 3, right? So a3 would be basically a2 plus like 2a1, right? And then if I wanted to get the next one, if I wanted to get a4, then I just need to plug 3 in here and then 2 in here, right? So I plug in, if I want 4, then it's going to be 3 and 2, right? If I wanted to get 5, then I just, can use 4 and 3. Okay, so this is fine, but I can also shift the sequence backwards. So for example, if I wanted to get 0, how can I get 0? I can plug in, if I plug in 2 and 1, I can get 0, right? So basically, if I take 2 and I plug it here and I 1 and I get 0, then I'm going to get the sequence backwards. I'm going to get the term with 0, a0. So this is the thing is, if your sequence starts at 1 or 2, always go back with the sequence and compute what a0 is by going backwards. You can also get so from here, if you were to do that, right? So if I were to plug in, this is going to be equal to 3, right? And this one is going to be equal to 1. So I get that 3 is going to be equal to 1 plus 2 times something. So you clearly get that this also needs to be a 1. And then we're done. So we got that a0 is equal to 1, right? You might say, but well, wait a second, a0 is not defined for this sequence. But you can always basically create like the new problem. You can say that, hey, with this parking spots, when n is greater or equal than 1, then the problem is just parking spots. But when n is less than, so basically you can say that, oh, I have 0 parking spots. How can I park cars in there? But the thing is, now this is a sequence problem. We're not solving the car problem anymore. What we did is we took the car problem and we converted it into a sequence. So the car problem is only the sequence for positive values. But the sequence can have negative values. It's just that it doesn't apply to the car problem anymore. The car problem only looks at the sequence, only looks at positive values of that, right? But see, the thing is, you can actually go down even more. You can also look at like the sequence, for example, -1. So if you wanted, for example, if you make this to be 1, and if you make this to be 0, then this thing here would just be -1, right? So you have 1, 0, -1, right? So then what could you do? Well, I guess you could plug in 1 is this one's going to be 1. So then what is going to be this sequence, a -1? Well, you see that this sequence is going to be 0. So actually we got a0 is equal to 1, and then a -1 is equal to 0. And then you can also try to compute a -2. How would I compute, a -2? Well, again, you can go backwards in time, right? So you can take any sequence and you can, move it backwards in time. So let me clear this a little bit. So let's compute a -2. So if I wanted a -2, I would plug in what? I would get 0 here, -1, and I get -2 in here, right? So a0 is going to be equal to 1. A -1 is going to be equal to 0. So then what does this one need to be? So it's 2 times something. So this one is going to be basically a 1/2. So I get that this one is going to be 1/2. You guys see? The thing is, so basically you can have negative terms in the sequence. So the sequence can also go all the way to -infinity. You can go to +infinity where you look at the next term, but it can also go to -infinity where you look at the backwards term. The way you can do it is you can basically write the sequence like this. So how can I get the sequence next if I knew the parents, how can I get the kid? So basically the one that comes before him. So you can rewrite the sequence in a slightly different way. You can basically say that, if I were to make this to be an, this would be, n plus 1, and this would be n plus 2. So basically, you can take this sequence and you can, what I'm trying to say is you can take this sequence and then you can rewrite it like this. You can rewrite this. That's going to be an plus 2 is going to be equal to an plus 1 plus 2 an minus an, right? So basically what I did is I added, plus 2 everywhere such that now this one is an. So now if you wanted to get from here, if you wanted to get an, you see that an is going to be what? It's going to be 1/2. And it's going to be the difference, an minus 2 minus an plus 1, right? So so this is basically the sequence, how the sequence goes backwards. So you take the previous terms, the bigger terms, an plus 2, an minus 1, you look at the difference, divide by 2, and you get the next one. So basically, if your sequence, if the starting conditions didn't start with 3 and 5, maybe the starting conditions started with A10 and A11. Then what you can do is you can move the sequence backwards, right? You can compute A9, A8, A7, A6, A5, all the way to A0. So always try to get A0, because if it's not too hard, always try to get A0, because A0 has this interesting property, right? A0 is just like summing up the coefficients, and then A1 is just going to be C1 lambda 1 plus C2 lambda 2. Okay, so now I guess if we go back to our problem, we have the coefficients were like what? 3 and 1, right? So let's try and figure out what are going to be the coefficients, C1 and C2 in this problem. Well, if I were to plug in, if I were to plug in 0, right? So A0 was equal to 1. So if I plug in 0, I get C1 plus. So I guess let's simplify this a little bit. So so I guess A0 is equal to 1, right? So C1 plus C2 is equal to 1. Okay, so this is equal to 1. And then what about the A1? A1 is equal to 1. So this one's also 1. Okay, so let's just look at this two. So what is lambda 1 and lambda 2? This was 3, and this was, minus 1. Okay, so I guess what can I do in here? So I have, C1 plus C2 is 1, and then 3C1. So I guess if I were to, simplify this, so basically 3C1 minus C2, right? So basically I'd have 3C1 and then minus C2 is equal to also 1. So I guess what I can do is I can add them. What's happening if I add them? Oh, sorry, I had this mistake. The roots are not, sorry guys, you should have, so what are the roots in here? So if I had 1 plus 3 is 4, so divided by 2, so it's going to be 2. And then 1 minus 3 is minus 2 divided by 2 is minus 1. So actually I have a small mistake in here. The roots are not 2, the roots are 2 and minus 1, not 3. So this should be 2 in here. Right, so yeah, you need to be careful. It's very easy to make mistakes in these problems. You can always check your answer at the end, but yeah, make sure when you solve quadratic equations you don't make any mistakes. Okay, so if I were to look at this problem in here, sorry, so in this case I would need to update this one. Is not a 3, but this one is a 2 now, right? So this would be basically a 2. So what would, and let's make it also red because we're using red color for this. Okay, so now what can I do? So I can, for example, add them. So if I add them, this and this would cancel. I would get a 2, and then I'd get 3C1 is equal to 2. So if I add them, I get like 3C1 is equal to 2. So basically, C1 is equal to 2/3. And now look, C1 is equal to 2/3, but C1 plus C2 equals 1. So I guess C2 is going to be equal to 1/3. So yeah, so that's basically it. I got 2/3, 1/3. So now what I do is I take this 2 and I plug them in here and in here, and then I'm done. So basically my answer is going to be what? It's going to be basically 2/3. 2/3 times 2 to the n plus 1/3 times minus 1 to the n. So basically this is my answer. And then, yeah, you plug in the numbers, plug in n equals 1. N equals 1, you'd get 4 times 2/3 minus 1/3. So you'd get 1, which is fine. You plug in n equals 2, you get, then you plug in n equals 10, you're going to get the answer, you're going to get A10. Does this make sense, guys? So basically it all comes from this idea, from this guess, an is equal lambda to the n, right? It all comes from like this guess, an equals lambda to the n, and in here, I guess an equals lambda to the n, right? And then the thing is that we notice is that when we do an equals lambda to the n, is there's like multiple lambdas. There could be a lambda 1 and a lambda 2. So basically, an has two options. It can be this one or this one. But the thing is, both sequences are good. So if you have two good sequences, you can always take two good sequences and combine them and you get another good sequence. You can add them, you can subtract them, you can multiply by them by any coefficients. It's still going to be a good sequence, right? So basically, yeah, this is kind of like the main idea here is you can combine two good sequences, you get another good sequence. So what is the most general way you can combine them? You can pick any coefficients, C1 and C2, to combine them, right? Okay, so this is kind of like good. All right, so I guess this is the first part of the class where we solve the problem with two of them, but there's actually a little bit more in here. So see in here I got two roots, lambda1 and lambda2. But what is happening when delta is equal 0? When delta is equal 0, there's only going to be only one root. So maybe I'll yeah, you know what, we'll get to this in a little bit. So let's do maybe a 2-minute break now. 2-minute break, and then afterwards we're gonna get in and get into the second part of the class. Okay, so yeah, let's go grab a cup of water, grab a snack, and then we'll do the second part of the class in 2 minutes. All right, so I guess let's get back into the second part of the class. So let's see, what have we discussed so far? So far we kind of like looked at, we saw that, there's problems with the sequence. And actually what we began with is we saw that, normally you can have problems that don't look like sequences at all. So for example, like problem 10.1 in here, where you need to move like stuff from one part to another, or like problem here with the parking lots, right? So you have like a bunch of parking lots, and you need to solve this problem. But we saw that what this problems had in common is that it's very easy to solve the easy cases, like the when n equals 1, n equals 2, n equals 3, right? So what we do is we have a starting condition. What is, the answer for 1, a1, the answer for 2, a2, and such and such and such. And then we notice that there's a relationship. So if I wanted to compute, the answer for 100, if I wanted to get a100, then a100 would basically be, some linear combination of the previous term. So if like you'd use a99, the answer for 98, the answer for 97, you'd put them in somehow linear relationship, and you're going to get the next one. So then from this, like by, practicing getting these problems, one thing that we got is that, more generally, we're interested in solving sequences like this. And when we look at the sequences and, we plug in some starting conditions, we see that depending on like what coefficients they have, for example, a 3 and a 2, we see that it almost doubles every step or triples every step, right? So we kind of like saw that these numbers, they grow really, really fast. So for example, here's the case with the Fibonacci number. So it would kind of like make sense to have a good guess that, an is exponential. It's like some constant to the power n, right? Maybe it doubles, maybe it triples or like whatever. It's just growing really, really fast. And then we saw that, okay, if I had some good sequences, well, actually, before we do that, we saw that, okay, if I can put in lambda 1 and lambda, like if I were to put in an equals lambda to the n, then, all the lambda higher powers are going to simplify. So just get the quadratic, right? Because you had only two terms. So if you simplify by lambda to the n minus 3, you get the quadratic, you can solve it, you get lambda 1 and lambda 2. But the interesting part is that both lambda 1 and lambda 2 are going to be good sequences, and this one is. And what we saw is that if you have good sequences, you can combine them, you can add them, you can subtract them to also get a good sequence, right? So that was kind of like our idea here, is that if this is a good sequence and this is a good sequence, I can combine them. I can, do plus, minus. In this case, it's enough to just write plus because I can replace C2 with minus C2, for example. So I can take any linear combination. So this would be my sequence, right? So then we kind of like afterwards, we looked at the practice problem where, like we got a sequence, we solved it, we got lambda 1 and lambda 2, we got that the sequence looks like this, and then we put in the starting conditions and we got from the starting coefficients. One thing that we noticed is that when we look at the starting conditions, sometimes the starting condition doesn't start at 0. It's nice to get A0 because for A0, you just get to sum up the coefficients C1 and C2. Right? But then the thing is, if you don't have A0, you might be tempted, okay, let's compute A2 and let's solve this thing here with lambda 1 squared and lambda 2 squared. But then what we discussed, the trick was that you can always, go backwards in time. So basically you can go forward in time. You can move from A1, A2, A3, all the way to like A1000, A1,000,000. But you can also go backwards in time. So you go from like, you can go from like A2, A1, A0, minus 1, minus 2, minus 3. So in some sense, you can also create negative terms in this sequence. For the car problem in here, the car problem doesn't care about negative numbers, so you can avoid those. You can only look at the positive number. But basically, by using 0, you can get like a nice equation. So always try to go backwards in time until you get a 0, and then solve this equation. It's going to save you a lot of time. Okay, so this is kind of like good. We did a lot of like good progress in here. So now there's kind of like couple more ideas that I wanted to discuss with you guys. So I guess there's the simpler equation. So the simplest equation is basically this. So like, let's write this. So like an. So if I could get, for example, like an is going to be equal to, for example, p an minus 1, right? So this one is very easy to solve because, if you were to solve this, you'd get that, that an is just going to be, equal to some, I don't know, basically it's going to be equal to p to the power n times some constant, right? For that constant is going to be basically a0. So basically, you get that an is going to be, p to the n times some constant. But I guess there's like the more general one is like when you have two terms backwards, right? So if you have an is equal to p an minus 1 plus q an minus 2. If you have this sequence, right? Then we get more generally that an is going to be, there's going to be two roots, lambda 1 and lambda 2. So it's just going to be c1 lambda, maybe I use a different color. So it's going to be basically, an is going to be equal to c1 lambda 1 to the n plus c2 lambda 2 to the n. But now here is sort of a question. What happens when lambda 1 equals lambda 2? So if you look at part 3 in here, if lambda 1 equals lambda 2, then what do we get? We kind of like get a troublesome situation. We get that an is equal to c1 lambda to the n plus c2 lambda to the n. So you get it c1 plus c2 lambda to the n. So it's just, c lambda to the n. So this is problematic because, look, this problem is going to have two starting conditions, right? So you need 2 degrees of freedom. Lambda is fixed. So in here, we could have adjusted C1 and C2, but in here, it's not enough to just have just one. So the question is, what is happening here? We're going to be able to like look at this. What is happening when the root is repeating itself? And then also like another case is like more generally, what happens if I have 3 terms or like more terms, right? So what if an, is basically, let's say like P1 an minus 1 plus, P2 an minus 2 plus P3 an minus 3. What if I had more terms, right? So what if I go k terms back? So Pk an minus K, right? What if I had like something like this? Then, what would be your answer? What would be our answer? an in this case. Okay, so we'll figure that out in a bit. So this is kind of like the things that we want to discuss. So this one, we already got it. This one, we got it. So now there's still this one and this one. And there's also like one more question in here. Question number 5 is basically what is happening when lambda 1 and lambda 2 are complex? So what if, basically, what if, so maybe I should write it just if. So if lambda 1, lambda 2 are basically complex numbers, right? Then basically they're like stuff like a plus So basically A plus IBI. So basically you see that if they're actually complex, lambda 1 and lambda 2, they have to be conjugates of each other. So you're going to be, so complex numbers always going conjugate. So, but the thing is, it kind of like gets complex because you'd get that, AN is going to be, C1 and then A plus IB to the power N, right? And then, you get C2 and then A minus IB to the power N. So for example, if I wanted to ask, compute me A 100, you'd need to come and take 100 and plug 100 here and 100 here. And see, it gets messy very easily because you're not going to raise this to the 100th power. So the question is valid. What's happening when lambda 1 and lambda 2 are going to be complex numbers? Okay, so we kind of like, we actually build a lot of fundamental stuff here. So these are going to be, like the 5 main questions. Actually, there's also a 6th question here. So this is when you have the sequence. This is simplest one. We ignore it. This one is interesting already. But one way you can make the sequence more interesting is like, what is happening? Part 6, when you add a constant. So for example, if you have a sequence AN, it's going to be equal to P AN minus 1 plus Q AN minus 2 plus some constant, let's say plus some constant T. So how about this sequence? How do I solve this sequence here? Because you see, guys, the guess wouldn't work anymore here, because if I were to plug in the guess, this would be lambda to the N is equal to P lambda to the N minus 1 plus Q lambda to the N minus 2, but then it's going to be plus T here. So I cannot simplify the lambdas. Normally I simplified and I got a quadratic. I got lambda squared is equal to, P lambda plus Q. But now you see I have this T. So if I were to simplify, this would be T divided by lambda to the power N minus 2, right? So this would be problematic. This is not a quadratic anymore. This is the issue. This T is the issue. This T in here is the issue. So the question is, what do we do about this thing in here when we have a constant? Right? When you have a constant question mark. And actually, you don't really need to have 2 terms. You can have only 1 term. So for example, I can say that, just plus T in here, right? If I just add a plus T in here, it already messes this one up because I cannot just say that, every single time I multiply by P because there's, a T here. So like more general like this, or also more generally, if you take this sequence that has, is looking back 3 terms, and this one also has a plus T in here, what is going to happen in here, right? So you see, when you add a constant here, it messes things up. So the question is going to be, how do we solve this thing when we add a constant? So there's, 4 more questions left to answer, but we're going to be doing them pretty quick. So let's start with question number 4, actually. 4 is going to be easiest in here. So look at this thing. So if I try to solve 4, maybe let's just like write it down with 3 of them. So imagine you had so a system that looks like, you had AN, right? So AN was equal to, I don't know, like 2 AN minus 1. So, or maybe I guess if you want, you can make it just like more general. So 2 AN minus 1 plus, I don't know, 3 AN minus 2 minus AN minus 3, right? So if you had a system that looked like this, and I guess this system still needs to have some starting conditions, right? So you would have some starting conditions. Maybe let's say 0 is equal to 1. Let's say maybe A1 is equal to 3, and maybe A2 is equal to 4. So you guys see what I'm doing in here is basically, because it has 3 terms that you look back at, to initialize the sequence, you need 3 terms. It's not enough to just say only 2 of them. 2 of them wouldn't be enough, right? You need the last 3. So I have to write down the 3 terms. Okay, so maybe I have the starting condition, I have this. How do I solve this? Well, same idea. You just make the guess AN is equal to lambda to the N, right? So you make this, guess. So now what do I do with this guess? Well, I just plug it in here. So what is happening when I plug this guess in here? I'm going to get a cube. So basically, I'm going to get lambda to the N is going to be equal to 2 lambda to the N minus 1 plus 3 lambda to the N minus 2 minus lambda to the N minus 3. So now what I can do is I can just simplify by lambda to the N minus 3, right? So if I simplify that, I get a cubic, right? So what's the cubic? The cubic is going to be lambda cubed. It's going to be equal to 2 lambda squared plus 3 lambda minus 1, right? And then I can rewrite this as like lambda cubed minus 2 lambda squared minus 3 lambda plus 1 equals 0. So this is basically a cubic polynomial, right? Cubic polynomial, right? Polynomial. Okay, so now what am I going to have in here? So guys, what you can see is that there's going to be 3 roots in here, right? When you're going to solve this, there's going to be, lambda 1, lambda 2, and then lambda 3. So there's going to be 3 roots in here. So now how can I solve my problem? Well, if you look at AN, now AN is going to have 3 options. So AN is going to be, can be either lambda 1 to the N, it can be either lambda 2 to the N, and it can be either lambda 3 to that, right? And it can be with any coefficient, C1, C2, C3. All of this would be good sequences. If you look at this sequence, this sequence, this sequence, all are good sequences. So the thing is, same way here that we had, 2 good sequences, I can add them. You can also like take combinations of three sequences. The reason we didn't take the combination of three sequences in this problem in here is because, if I had the third sequence would always already be a combination of these two sequences. So there was no point to take a combination of these two sequences in the third one, because the third one would always be a combination. But then actually in this problem, you'd get the three sequences that would all be different. Like this sequence here is not a combination of these two sequences because the lambdas are different, right? There's going to be the question, what's happening when lambda is repeating? So we're going to take a look at that. But in this case, all the sequences, they're kind of like different, so they're independent. So what it means is that you can take any combination of them. So basically, the more general solution is going to look like this. So an is going to be equal to, C1 lambda 1 to the n plus C2 lambda 2 to the n plus C3 lambda 3 to the n. So basically, this is going to be your coefficients. And then you take the starting conditions. You're going to take, your starting conditions, and you're going to like plug them in here. You're going to plug in n equals, 0, 1, 2. So you're going to plug in 0, 0, 0, 0, and you get a relationship. C1 plus C2 plus C3 is the first one, right? The thing is, this gets more complicated. And then you can plug in 1, 1, 1, 1. And then you can plug in, 2, 2, 2, 2. And you take the starting conditions, and you have three systems. You have three unknowns. The unknowns are the coefficients, C1, C2, C3. The lambdas you already know. And then, yeah, basically you can solve it. So I would say this, guys, 90% of the time, or maybe 95% of the time, maybe 95% of the time, you're going to have to solve quadratic equations. You're only going to have to deal with quadratic. So this is like 95% of the time you're going to be in this equation, right? So don't stress too much. Like 95% of the time, you're just going to need to know how to solve a quadratic. Now, there's going to be 5% of the time. 5% of the time, what's going to happen? 5% of the time, maybe you're going to get like three terms back. So you're going to get a cubic. So in 5%, so maybe this is something like 5% of the time. So now the thing is, you're going to need to solve it. So how do you solve this cubic, right? So the cubic is usually a little bit harder to solve, but whenever you have to deal with cubic, basically make the guess that like almost like 80% of the time, one of the solutions is either going to be, 0, plus minus 1, or like plus minus 2 is a solution here. So basically you have to try in, lambda equals 0, 1. So basically you take, let me clear this a little bit. So basically what you're going to want to do is you're going to want to take this and plug this in here. Try in 0, 1, 2, right? And see if this is a solution. And then you know that you guys can factorize this. So if you take a cubic, right, this cubic can be factorized as like, lambda minus lambda 1, lambda minus lambda 2, and then lambda minus lambda 3, right? So basically, if you take the three roots, this can be factorized, right? So then if you figured out that one of the roots was 1 or minus 1, you can just plug it in here. And you can take this polynomial and you can divide it, right? So if I take all of this polynomial and I divide it by, let's say that one of the roots was 1, right? Then I can take all this polynomial and I can divide it by, lambda minus 1. Then I'm going to get the second degree polynomial that's going to have two roots, lambda 1 and lambda 2, plus the third root, that's 1. Right. So basically, if you want to solve, this is kind of like different from what we're discussing, but if you want to solve a cubic, there is a formula, Cardano's equation that like gives you like what the equations are. Those are a bit more complex, and we can make a separate class about that. But in order to like skip that and be like really fast, most of the time you can just guess the roots. At least you can guess one root. You can try plus minus 1, plus minus 2, and see if any of this works. Most of the time it's going to work. If it doesn't work, then learn how to solve cubic equations. But if it works, then you're done, because if one of the roots was 1, then you can just divide by lambda minus 1. So you take this polynomial, divide by lambda minus 1, you've got the quadratic. So then you need to figure out the other two roots, and you're done. Okay, so this is 5% of the time, is like when you have 3 of them. But now this actually, there's also 1% of the time, or maybe 0.01. Like I don't think I've seen any problem in the EMC12. But, it could be the case that instead of having just like 3 terms back, you could have like 4 terms back or 5 terms back. So you can have, like a bigger number of terms back. So the question is, what's happening more generally when you have n terms back, right? So basically, let's imagine that you had a sequence that looks like this. So if you had an was equal to, I don't know, like, P1 an minus 1 plus P2 an minus 2 plus, Pk an minus k. So maybe, my sequence looks back k terms, right? Then, well, in this case, you're going to need the starting conditions. You're going to need the starting conditions a1 through ak, or 0 through ak minus 1. And then also, same idea works. So basically, you are going to do the guess, an is equal to lambda to the power n. So the same idea. Now, what happens if I plug this in here? I'm going to get, lambda to the n minus p lambda to the n, p1 lambda to the n minus 1 minus p2 lambda to the n minus 2. So what I'm doing is I'm taking all of this stuff and I'm moving it on the other side. And then minus pk lambda to the n minus k, right, is equal to 0. So this is what? This is a polynomial. Well, you may say that this is a polynomial. Sorry, so let me clear this up a little bit. And minus k is equal to 0. So you may say that this is a polynomial of nth degree, right? Nth degree. But what you can do is you can always simplify by lambda to the n minus k, right? So if I simplify by this lambda, what do I get? I'm going to get, lambda to the k, right? Plus, minus p1 lambda to the k minus 1, plus, minus p2 lambda to the k minus 2, minus, and it keeps going like this, minus, pk lambda to the 0, right? Is equal to 0. So you see, this is a kth degree polynomial. So kth degree polynomial. So it's going to have k roots, right? So if you're going to try to solve this, you're going to see that it's going to have k roots. So this is 1% of the time. So 1% of the time. So very, very unlikely you're going to get it. But if you get it, somehow you need to figure out what the roots are. But let's say that you're really good at solving kth degree polynomials, then, you could figure out what these roots are. So you just get, I don't know, some roots that are let's say, lambda 1, lambda 2, lambda 3, all the way until lambda k, right? So this would be your k roots. Okay, so then you would say that, then an can have a bunch of options. An can be, it can either be c1 lambda, it can be lambda 1 to the n, or it can be some other coefficient c2 lambda 2 to the n, and it can be all the way until ck lambda k to the n. All of these are going to be good sequences. This is a good sequence, this is a good sequence, this is a good sequence. So you can take any linear combination of them. Well, I guess I already wrote the coefficient. So I guess the more general solution from here is going to be this, that, if you wanted to figure out what an is, then an would just be, c1 lambda 1 to the n, plus c2 lambda 2 to the n, plus, and then ck lambda k to the n. Okay, and then basically, the lambdas we already know. The only thing that's missing is c1, c2, ck. So how do we know those? Well, those come from the starting conditions, right? Because look, if the sequence needs to look k terms back, I need to tell you the first k term. So basically, I need to tell you what is a0, a1, a2, all the way until ak minus 1, right? I need to tell you what these terms are. And then you take them and you plug them, you plug in n equals, 0, 1, all the way until k minus 1. In the starting conditions, and then you solve what the coefficient is going to be. It's going to be much more complex, but you can somehow get it. Okay, I guess so. This is kind of the main thing about the second part, right? So if you have more terms in your sequence, you're just going to get more roots. So more roots just going to make it more complicated. This is probably 1%, less than 1% of the problems are going to be like this. But sometimes maybe 5% of the time you're going to get cubics. So you should at least know how to do the cubics. But the reason I'm mentioning it is because there's nothing different. The same strategy just applies. Okay, cool. So we basically got this one here as well. Okay, so now we still have a little bit more stuff to do in here. So we've got this one, we got this one, and we've got this one. So let's see, which one should we do next? I guess let's do free, because free sort of comes naturally in here. Or actually, well, free is a little bit tricky. So maybe it makes sense to, let me do 5 for now. So 5 is using basically complex numbers. So 5 is actually, it's not that hard. It's just basically you need to use the polar form of the complex numbers. So if you work with complex numbers, right? So let's say that I had a quadratic equation. So maybe my quadratic would look like this, a lambda squared plus b lambda plus c is equal to 0. So this is my quadratic, and I need to solve it, right? So basically, I'm going to get two roots, lambda 1 and lambda. So basically, I would solve this. So I'd get, the delta is less than 0. So I'll get two roots, lambda 1 and 2. This would be equal to basically minus b plus or minus square root of delta divided by 2a, right? So this would be basically x plus or minus iy. So this would be basically the real part and the imaginary part. And you guys see what's happening? The complex numbers, they're always gonna come in pairs. So you're gonna have, complex number x plus iy, and there's going to be the other one is going to be x I minus y, right? So basically, if ABC, so this is kind of like the fundamental theorem of algebra, which says that, if I give you a quadratic, there's going to be 2 roots. If I give you a cubic, there's going to be 3 roots. If I give you a 10th degree polynomial, there's always going to be 10 roots. It's just that some roots can repeat themselves. They can be double roots, triple roots, 4 times. And also some roots can be complex numbers, right? So, but the thing is, if the roots are complex numbers, they always have to go in pairs. So if I gave you a cubic and one of the roots was 5 plus 3i, the other one would need to be 5 minus 3i, and then the other one would be some real number, right? So the complex numbers, they always go in pairs. Okay, so now why is that the case? Well, the reason is because so if lambda1 and lambda2 are the roots, then what you can do is, you guys know that you can factorize this, right? So I guess I haven't discussed this, but if you have two roots, lambda1 and lambda2, this can always be factorized as like a lambda minus lambda1, and then lambda minus lambda2, and then from here you're going to get Vieta's theorem, right? So basically these two are basically the same. But then the thing is, if you open up the parentheses in here, if you open up the parentheses, what you're going to get? You're going to get a, and then inside you're going to get, lambda squared, which is this thing in here, and then you're going to get plus, or maybe, I can just write it lambda squared, and then you're going to get, so you're going to get basically you're going to get plus a minus lambda1 minus lambda2 lambda, and then you're going to get also plus a lambda1 lambda2. So what you end up getting is that this is exactly Vieta's theorem. So basically you get that this term here is going to be the term b, and then you're going to get that this term here is going to be the term, so sorry, not all of this, but all of this term here is going to be the term c. So this is exactly just Vieta's theorem. So you can think about that. But the beauty of this is that, see, when I add this two roots, so here lambda1 and lambda2, when I add them together and with a minus in the front, when I add them together, the imaginary part is going to cancel. And when I multiply them, remember, when I multiply them, what do I get? So if this is, the numbers, it's going to be z and z conjugate, right? So when I multiply z times, z conjugate, what do I get? I'm going to get, the norm of z squared, which is basically going to be, x squared plus y squared, right? So it's a real number. So basically, yeah, they go in complex numbers, but then they simplify nicely. Okay, so let's forget about this for now. So now here is my question: is like, what is happening in this case? Like when I have the numbers like this, I have, this is, c1 to like some lambda 1. So this is just, going to be my c1 lambda 1 to the power n plus c2 lambda 2 to the power n. But lambda 1 and lambda 2 are complex, so I need to raise them to the power n. So what do I do in here? Well, here comes the polar form. So remember, when I need to raise a complex number to a high power, I need to use the polar form. So basically I do r e to the I alpha, right? So it's going to be r1 e to the I alpha 1 plus r2 e to the I alpha 2, right? So this would be basically my alpha 1 and alpha 2, and I just need to plug them in here. So let's basically work for this. So let me make a separate page. So let's say that I got two roots, lambda 1 and lambda 2 are the two roots, right? So maybe, I don't know, like lambda 1 and lambda 2. So, okay, so maybe, lambda 1 is going to be equal to, yeah, so let's write them down like this. So I would have what? So I would have, lambda 1 is equal to, x plus iy. So it's going to be equal to r1 e to the I alpha 1. So, and I can also write in the sine and cosine form, right? So e to the I alpha 1. And it's also going to be equal to, I guess what? It's going to be equal to r1 cosine alpha plus I sine alpha, right? So this is like the thing I can do for alpha 1, lambda 1. And this lambda 2 is going to be x minus iy, because the complex numbers always go in pairs. So it's going to be r. But actually, look at the r. They're both going to share the same r. So if you think about like graphing these 2 points, it's going to be like this. So this is going to be coordinate x. This is going to be coordinate y. This is going to be coordinate minus y in here. So if you think about like these two roots, lambda 1 and lambda 2, they're going to be, this is going to be x minus iy. This is going to be x plus iy. So the thing is, they're going to have the same radius, right? The radius is going to be x squared plus y squared. So it's going to be the same radius. So instead of writing r1, I can just like write the radius, right? So it's going to be the same radius. So let me just write it like that. So because they share the same radius, it's going to be the same radius. So it's going to be r e to the I alpha 2. But if you look at like alpha 1 and alpha 2, alpha 1, so because they're complex conjugates of each other, right? Like this is going to be alpha, this angle. So if you go that way is alpha, this way is going to be minus alpha, right? So if you go counterclockwise, it's plus alpha. But if you go clockwise, it's going to be minus alpha. So basically alpha 1 and alpha 2, they're going to be plus alpha and minus alpha. So let me just, I guess, do that, right? So basically what are going to be the angles? So this one's going to be, I guess in our case, it's going to be I alpha, and this one's going to be minus I alpha. So it's going to be, r, cosine. I guess I should write what? I should write minus alpha plus I sine of like minus alpha, right? But the cosine doesn't care if it's plus or minus. So I can just write cosine alpha, but the sine alpha minus alpha cares, like the minus just comes in the front, right? So I can rewrite this. So let's rewrite this. So I can rewrite this as like cosine alpha minus I sine alpha, right? Okay, so I've got this thing. So I've got two complex numbers. Okay, so now let's take and see what is happening when I take these complex numbers and I plug them in my equation. So remember, what did I say for my sequence AN? So I said the following, that, my sequence AN. So if I had my sequence, I had my sequence AN, and I said this is going to be, some C1 lambda 1 to the power n plus C2 lambda 2 to the power n. Well, if you look at this, there's two options I can do. I can either write this as like C1 and then you write x plus IY, x plus IY to the power n plus C2, x minus IY to the power n. But see, raising this to the power n and this to the power n is messy. You don't want to do that. Like if you want to, if I wanted to raise this to the power n, this to the power n, I would either like raise this and this to the power n, but this would be messy. But what I can do is I can raise this to the n, and this is just going to become n alpha and n alpha. So this is nice because you get an n here and an n here, you have an n here, and you're going to have an n here and an n here, right? So if you actually raise them to the power n, you want to use the polar form. This one is much nicer. So what I can do is, instead of using this one, I can rewrite that this is, this is just going to be, C1. And then what about lambda 1 to the power n? Well, lambda 1, I'm just going to use this formula here. So I'm going to write it as like, r to the power n. And then I'm going to write, cosine of alpha n plus I sine of alpha n, right? So this is going to be the first term in here. This is going to be this term here. But okay, I've got the second term in here. So it's going to be plus, and the second term is going to be C2. And it's going to be, again, r to the n, but it's going to be cosine alpha n minus I sine alpha n. Okay, so I got the first term here and I got the second term, this one. What's happening if I add them? Well, guys, look at this. There's two things in here. There's the cosines, and then there is the sines, right? So why don't I just put them together? So if I put the cosine alpha n, so cosine and alpha, what am I going to get? I'm going to get, okay, so r to the n is kind of like the same everywhere. So I'm going to get this thing here. I'm going to get, r to the n C1. So I'm going to get this thing. So C1 plus C2. And then I guess, I'm going to have an r to the n cosine of n alpha. Plus, I'm going to get, this thing here. When I sum this two up, what do I get? So sine alpha comes in the front. So it's going to be C1 minus C2, right? So it's going to be, C1 minus C2, r to the n. And then it's going to be I and multiplied by an I, and then it's going to say sine alpha, right? But now here is the thing, guys. So one thing that I can do in here is I can take this thing and I can call this thing in here. I can take it and I can call this D1. And I can call this thing in here, the entire thing in here, I can call this thing D2. So now what's going to happen is that I can rewrite this entire thing. So I can basically say that, AN is going to be equal to R to the power N. And then inside, I'm going to write, D1 cosine of N alpha. So it's going to look like this. So cosine of N alpha plus, D2 sine of N alpha. So this is basically the formula. So if you have to deal with complex numbers, then your AN, you don't use this guess here anymore. You don't want to use this anymore because this one is messy, right? Like you don't want to raise this to the power n. So you want to avoid that. So what instead you want to do is you want to work with this one, sines and cosines. So it's going to be two coefficients, D1 and D2. But you may say that, like, wait a second. Well, AN is like just real numbers, right? So maybe, I don't know, like I gave you like a relationship, and maybe, I don't know, like, let's say that A1 is equal to 1, and then maybe A2 was equal to 3, and then you can keep computing them, right? So basically you can say that, oh, all of these are integers, but this has like sines and cosines. These are not going to be integers. But the thing is, maybe the cosine is not an integer, maybe the sine is not. But when you're going to combine them, you're going to see that, all the stuff that's like fractions and square roots and stuff, all the stuff is going to cancel. So the only thing that you're going to be left with is you're going to be left with integers. So all the stuff is going to simplify. Now you might say that, okay, wait a second, but I also have like complex numbers in here. These are like all real, but like, what if I get complex numbers in here? And you may say that, okay, here I have C1 and C2, and they give me D1, but then here I have an I, right, that comes in front of C1 and C2. But the answer is going to be that C1 and C2, actually the coefficients here, they're going to be complex coefficients. So the way this works is that because lambda 1 and lambda 2 are going to be complex, the coefficients C1 and C2 are also going to be complex. But the thing is, when you raise this to the power n, you raise this to the power n, these are complex, so you open up the parentheses, you're going to get a bunch of complex numbers, but then all the imaginary parts are going to cancel. So the C1 and C2 are going to be in such a way, complex numbers, that all the imaginary parts are going to cancel, so everything is just going to be a real number. So basically, it's going to be in such a way that C1 plus C2 gives you a real number, but then C1 minus C2 gives you an imaginary number. And when you multiply it by I, you get a perfectly real number. So basically, this thing here is real, this thing here is real. The way you can see this is that if C1 and C2 are complex conjugates of each other. So, imagine that, C1, like what if, we had something like this. Let's use what color? So light blue. So if C1 was equal to A1, or maybe, yeah, so this A1 is not related to that A1. So maybe, C1 was A plus IB, and then C2 was equal to A minus IB. Then look at this. If I were to do C1 plus C2, if I were to do C1 plus C2, I would just get 2A, right? And if I were to do C1 minus C2, I would get, 2IB. But then if I were to multiply this by an I in the front, then this would be I squared, right? So this would be just like minus 2B. So basically what I'm trying to say is that, C1 and C2, they're going to end up being also complex numbers, but complex conjugates of each other, such that when you add them, you get a real number, you get D1. And then when you multiply them, sorry, not multiply, but take the difference, you're going to get, 2I squared B, which is just 2B, which is also a real number. Okay, so this is kind of like the main idea in here. Okay, so just give me a moment, guys, and we'll do some more stuff. All right. All right. Okay, so we did the complex numbers. So I guess we can probably do a problem here with you guys. So let me make a check in here. So we covered the stuff with the complex numbers. So I guess what should we do when we have complex numbers? So I guess when we have the complex numbers, if I clear this one up, this is actually, instead of like doing this, you should actually write this as like, this is going to be, equal to some R to the power N. And you're going to write it like this, like D1 cosine N alpha plus D2 sine of N alpha, right? So this is going to be your answer. So I guess if you guys want to do a practice problem, right? So what can we do for a practice problem? So I guess I should already share this link. There's another resource, Brilliant, which has amazing stuff here on linear recurrences. So I guess you can, if you look at Brilliant and you look towards the end, there's a problem here with complex numbers that discusses. So for example, if you had this sequence here, right? And let's say that the sequence starts with 0 and 1, and it looks like this. Well, if you tried to solve this, you'd get a characteristic equation. You'd get something like this, like lambda squared is equal to lambda minus 4. So you try to compute delta, and you'd get that, like delta is going to be, 15. So it looks messy. It looks like lambda 1 and lambda 2 are going to be two complex numbers in here, right? So they're going to be basically 2, and then it's going to be cosine of, like theta plus minus I sine of theta, right? Where theta, what is theta? Well, theta is going to be this thing that gives me square root of 15, right? So arctangent. So basically, how can I get theta? Well, it's going to be like a triangle that looks like this. So it's going to be, because it's going to be 1. This is going to be square root of so actually the opposite one. So it's going to be 1 here. This is going to be square root of 15 here, right? So this is going to be your theta. So if you want a tangent theta, this would be, I guess, what? It would be just square root of 15, right? So I guess what is theta? So theta is going to be, arctangent of 15. Well, anyways, it doesn't matter. So the thing is, you got some numbers and you can figure out what theta is. So most of the time, it's going to be some nice angle, maybe 30 degrees, maybe 45 degrees, maybe 60 degrees. So most of the problems, 90% of the problems, you're going to get a nice angle. Maybe, I don't know, 1% of the problem, there's going to be some ugly number. You don't have to do that. But the thing is, you just like write this thing with theta. And then I guess what can we do in here? So I guess what you do is you can also compute the radius, right? So the radius in here, you see that the radius is going to be 15. If this is going to be this squared plus this squared, so it's going to be 16. So you take square root, so the radius is going to be, I guess 4, and then it's divided by 2. So actually the radius ends up being 2 in here, right? So basically, the formula is going to look like this. It's going to be, like xn is going to be, is this radius to the power n, but then with two coefficients, C1 and C2, and then cosine n theta and sine n theta. So now you need to figure out, okay, what is going to be theta in here? What are going to be the coefficients? And well, this is actually also nice, because if you have this situation in here, you can plug in n equals 0 and then n equals 1. What do you get for n equals 0? So when you plug in n equals 0, you get cosine 0, which is just basically 1. And what about sine 0? Sine 0 is just 0. So this just disappears. So what you get is you get this thing that, or maybe I should have just like actually explained it in here. So if you look at this thing in here with sines and cosines, So if I plug in, this is an. So if I look at like so what is going to be a0? This is why it's nice to compute a0. So if you want a0, it's going to be r to the n, and this one is just going to become, this is 0, so it's going to become 1. So it's going to be r to the n d1 plus, well, what is this thing? This is going to be sine 0, just disappears. So yeah, so you just get it. So basically, if you want to compute, if you plug in 0, you get a0 is going to be this. So if you want to figure out d1, is just take a0 divided by this, right? And then if you plug in a equals 1, I guess if you plug in a equals 1, you're going to get sine of alpha cosine of alpha. So you're going to have to solve that. But the thing is, you got d1 very easily and you can get d2. So if we were to look at like this linear recurrence in here, see, I got two coefficients, c1 and c2, this coefficient. So I just can plug in n equals 0. So I get that the entire thing should be equal to 0. So I get that this coefficient c1 is equal to, so basically, yeah, if I plug in n equals 0, this just disappears in here, right? This is going to become a 1. So this is going to become x0, but x0 is just 0. So what do I get? I get that this coefficient needs to be a 0. Okay, so I got the first coefficient is a 0. Okay, so that's nice. So if the first coefficient is a 0, it means that I can just forget about this term. So it means that xn is given by this equation. And then I plug in n equals 1. So I plug in 1 in here, and I plug in 1 in here. And I get, what? I guess sine theta. I know what sine theta is. How can I figure out sine theta? So see, the thing is, you don't even need to know what theta is. The thing is, if you had something like the number that looked like this, and you knew that this was square root of 15, and you knew that this was like a 1, well, if you wanted like, theta, and if you wanted sine theta would just be, well, I guess, this is 1. This is, what is this? It's going to be, Pythagoras theorem. So 1 squared plus 6 plus 15 is 16. So this would be basically 4, right? So the radius is 4. So sine theta would just be what? Would just be this divided. So it would be 4 divided by square root of 15, right? So just take this, plug this in here, and you get that x1 is equal to 1, So, okay, so from here you get, you plug here 2 to the power 1. So you get C2. So what is C2? C2 is going to be 2 divided by square root of 15. Okay, wonderful. Then we have that, xn is just going to be, we say that the first term is missing because the first coefficient is 0. So it's going to be the second coefficient, 2 divided by square root of 15 times 2 to the n sine of like n theta. That's it. So this is basically, the term. So now you can plug in, so you get like basically this thing here. So now you can plug in n equals 1, n equals 2, n equals 3, and you're going to get a bunch of numbers. And what you're going to see is that all the numbers are going to be actually like integers. Like this angle theta is like so nice because, when you double it, when you triple it, you're going to get that this square root that you're going to get in here is going to cancel exactly with the square root in here. Because sine theta is 4 over square root of 15, c, and then 2 over square root of 15. So you can cancel them, and, square root of 15 is going to cancel on both sides very nicely. Sorry, I think I had a mistake in here. This is not the 4 over square root of 15. This is the opposite. So sine is going to be this side. So this side divided by this side. So it's actually square root of 15 divided by 4. So square root of 15 divided by 4, right? Okay, so yeah, you see that you take this thing in here and you plug it here. The square roots of 15 are going to cancel. So now if you look at sine 2 theta or 3 theta or 4 theta, again, square roots of 15 are going to cancel. So you're going to end up with like only real numbers. Sorry, integer numbers. Okay, cool. So I guess this is the main idea. Let me put this link here in the chat as well. So Brilliant is a great resource. It discusses like the same ideas that we discussed in a slightly different manner. Okay, so now if we go back to the whiteboard, I guess we are done with, we made good progress here. So let's see. So I guess we discussed complex numbers. There's two more things that we need to discuss in here. What's happening when lambda 1 is equal to lambda 2, and then what is happening when we have this case. So I guess we are a little bit over time. So if you guys need to go, that is fine. But I'm basically gonna explain probably like go for like another like 15-20 minutes, try to explain what is going on in these two cases. If you are like busy, you can just watch the recording later. So let me maybe, okay, I'm gonna leave this case with lambda 1 and lambda 2 towards the end, but let me look at like this case in here. So what is happening when I have a constant t, right? So okay, so this is a good question. So if I had the simple system, right? If I had a simple system that looked like, an is equal to p an minus 1. Okay, this is good because if I had this relationship, I can say that, okay, this is how many starting conditions I need. So the starting condition will just need to tell me what a0 is, right? So maybe a0 is like, I don't know, 7, whatever. I need just one starting condition. So, okay, so I can keep going down, right? So I can write this as like p squared an minus 2. I can write this as like p cubed an minus 3. And then I can just keep going, right? So I can eventually get to like Pn and then a0 in here, right? So then in this case, it's just going to be Pn times some constant k. That constant is just a0, so right? So you can just like plug in, for example, 7 if you wanted. Oh, okay, so this is kind of like easy. So you see right away where the idea comes from, that an is going to be lambda to the n times some constant, right? Okay, so this lambda is just like this coefficient in here that's like doubling or tripling or quadrupling or whatever it is. Okay, so now I guess let's think one step higher. What if we had, a constant t? So if I had, if I had, a sequence, let's write it like this. So if an was equal to p an minus 1 plus some constant t. Well, how can I solve this one? So you see, this one is a little bit troublesome. So maybe let's call this constant t. Let's call this constant. Let's make this constant to be 5, right? What could we do in here? Well, so ideally, what I could do is I can actually convert from this sequence, from the sequence an, maybe I can create a new sequence bn, such bn is going to be p bn minus 1. So I'd want to move from this bad sequence. So this is bad. So this is like bad, but this one is like good, right? So somehow I want to take a bad sequence and I can want to convert it into a good sequence. So there is actually a very simple trick in here. What you can do is you can take an and you can call this is going to be a new sequence bn plus some constant k. And then all you just need to figure out is you need to figure out what is this constant k. Well, what would happen if I take an and I call it like this? Well, then if I look at this sequence, this would become, so I want to take the bad sequence and I want to make it good. So what I do is I can just take an and shift it by a little bit by some constant k. So what would this k, I guess, be? So maybe I can give you guys like exact numbers. So maybe instead of like working with p, maybe I just give you exact numbers. So maybe, it's like tripling at every step, but now it's also adding a 5. So I want to somehow make it a good sequence. So what could I do in here? So I could take, an. So if I were to do that, I would get what? So an replace it with bn plus k. So I'd get, bn plus k is going to be equal to what? 3. And then, it's going to be bn minus 1 plus k plus 5, right? So, okay, so now look at the sequence. So what I want to do is I want to keep simplifying it. So I have the sequence like this, which is good. This one is bad. Actually, you know what? To make this look even nicer, what we are going to do is whenever you have a constant t, we're going to keep always this constant at the end. So basically what I can do is I can rewrite it like this. I can say that this minus this. So let me rewrite the entire sequence. So you're going to see why I do this. In a little bit, it's going to become obvious. But look, if I were to do basically move all the stuff on one side and keep the t on the other side, right? I want to keep it like this. So basically, this is my constant t that I added at the end. So I move all the stuff that's normal on this side, but the stuff that's bad on the other side. Okay, so if I were to do that, see, I want to somehow get rid of this t with this shift k. So what actually I could do in here, so if I simplify this, how does this simplify? So I would get, I'd get stuff like what? I'd get, bn plus k minus 3 bn minus 1 plus k is equal to 5. Okay, so now I can simplify and just keep this part in here. So I can write this as like bn minus 3 bn minus 1 plus k minus 3k is equal to 5. And now look, guys, what I have. If this thing were to be equal to 0, right? If I were to have the good sequence, so look, in the good sequence, this is equal to 0. So if this thing is equal to 0, I would need to have that this one needs to be equal to this one. So basically, this two would need to be equal. Does this make sense? So, okay, so now what is going on in here if these two are equal? Well, then I get what? From here, I can, just take this and like plug it, so from this equation, what would I have? So I would have, what is k? So I'd get, I guess minus 2k is equal to 5. So basically, I get that k has to be equal to minus 5 divided by 2. So yeah, so basically, if I were to use this transformation, what would I get? Then the entire problem would just basically become this: bn is equal to 3 bn minus 1, right? Okay, so now this is nice because from this problem, I get what? I get this is going to be, so I can keep going. So this is just going to be 3 to the n b0, right? And then let's say that I knew a0. So a0 was equal to 7. Then I can also compute b0. b0 is going to be 7. Well, what's going to be b0? It's going to be a minus k, right? So basically, you can compute b0. So you can say that, b0 is going to be equal to a0 minus k. So b0 is going to be equal to, I guess, 7 plus 5 divided by 2, right? 5 divided by 2. So, well, the point is, so 5 divided by 2. So the point is that, whatever a0 you had, you can always switch to a new sequence b0. So now this is nice because you just get this, right? So now look, this is a Bn. So what is Bn? Bn is going to be, an minus k, right? So basically, if you look at this thing in here, look, this is going to be equal to 3n, 3 to the power n. And what is b0? B0 is going to be, a0 minus k, right? But what is an? An is going to be equal to bn minus, sorry, bn. Bn is going to be an minus k. So I can write, an minus k in here is going to be equal to this. Okay, and now we are pretty much done because look, I'm going to look at this last thing in here and this last thing in here, right? And well, the two of them have to be equal. So Bn is this nice sequence that satisfies this nice property. So I just replace, I convert. So what I do is I take An and I convert to Bn. And then Bn is very easy to solve. So how do I convert between An and Bn? Well, I do An minus k gives me Bn. Bn is a nice sequence, solve it nicely. And then I convert, the last term B0. I'm going to get it from A0, right? So I know the conversion. So now I can have, there's a nice combination between Bn's because it's a nice sequence. And then I can just convert back to An. So this is how basically I get rid of this, this constant 5 in here that was a mess. So I guess the thing is you only need to compute this constant k. How do you compute the constant k? You just plug in here. So you just look at the coefficients. So you have 1 minus 3. So it's basically, it's going to be 1k minus 3k in here, right? So it's going to be 1k minus 3k. So you get minus 2k is fine. Okay, so if I simplify this, I guess last thing, what am I going to get? So I'm just going to get, that if I wanted to compute An would just be equal to, I guess, 3 to the power n, it would be a0 minus k, and then plus k. So yeah, so basically this is the formula for how you would compute. The only thing that you need to do is basically this coefficient 3, you need to solve the nice equation b, so you get this coefficient, and then you need to figure out what k is, and k is very easy to figure out from here. Now, okay, I guess we solved the general question when there is just one term look back, right? So what we just solved was the easy problem, where I had where let's say I had a plus t in here, right? If I had a plus t in here, but well, what's happening if I add a plus t in here? Or what if I have the more general problem? What if it's this problem plus t? What would happen? Well, it turns out that you can do the same transformation with k. So the way you do it, so if we were to generalize this, right? What would we have? So we're almost done. So basically, I would have, let's say that An was equal to P1. It was equal to P1 An minus 1 plus, Pk An minus k. Sorry, let's maybe call it, Ps An minus s, right? So I just have s terms look back and then plus some number t. Then one thing that I do, okay, let's move all the p's on one side. So let's take all the coefficient, all the stuff with a on one side. So let's write it like, if you're given an equation like this, you can rewrite it in what form? You can rewrite this equation like this. So An minus basically P1 An minus 1 minus P2 An minus 2, right? And then minus, and then you're going to write minus Ps An minus s, whatever, right? And then this entire thing is going to be equal to some t. And now this t is nice. Sorry, it's not nice. It's bad because it's messing things up. So what you can do is you can, get rid of this t. How can you do it? Well, you make a conversion, right? So your conversion is going to be that basically An is going to be, Bn plus k. So what is this shift k that I needed to compute? Well, you just plug in An, you plug this in here, you plug this everywhere, in here, and in here. So what do we get if we were to do that? Remember, my goal is I want to get a nice sequence, right? So what is the nice sequence? Well, the nice sequence is I want to get this sequence Bn minus P1 Bn minus 1 minus P2 Bn minus 2 minus Ps Bn minus s equals 0. So I want to get from sequence A, I want to get to sequence B that is nice, that doesn't have any t's, because this one I can just guess Bn is equal to lambda to the power n. So I can just do the normal guess, right? So you get Bn is equal to lambda to the power n. You just take this, you plug this in here, and you just get your like normal equation, right? That you can solve. You're going to get lambda 1. So we know how to solve B. So you need to solve the sequence B, but the sequence A is messed up by this extra A in here. So the thing you can do is you can just take An and replace it everywhere with Bn plus k, right? So okay, so what would I have? So I would have this Bn plus k minus P1 Bn minus 1 plus k minus P2 Bn minus 2 plus k, right? Minus minus Ps Bn minus s plus k is equal to t. Okay, so now if I put all the stuff with k on one side, the stuff will be on the other side. So if I keep on just the stuff with b, so the stuff with b is going to be bk minus p1 bk minus 1 minus p2 bk minus 2 minus minus ps bk minus s. Okay, so I put all the stuff with S on one side. And now what about the stuff with K? Well, what do I have with K? Well, I'm gonna have K and then another K with P1 and then another K with P2 and then another K with PS. So what's gonna be the stuff with the Ks? Well, it's gonna be plus K. And what's gonna be here? It's gonna be 1 minus P1 minus P2 minus P3 then minus PS. And this entire thing is equal to T. All right, so now what do we want? Well, we want a good equation, right? So we want this thing in here to be equal 0. So if I want this thing in here to be equal 0, basically, what I want is I want this thing in here to be equal 0, right? So how can this thing be equal 0? What K should I pick? Well, you can clearly see what K you should pick, right? If you pick exactly this K, if K is equal to exactly this thing, then this stuff in here is going to cancel with this. So you're just going to get that this thing in here needs to be equal to 0, right? So this is basically telling you, so what I'm doing here is I'm explaining to you how to compute K. So K depends on this coefficient. Is that, and why do you get a 1 in here? Well, it's a 1 because that's the coefficient of A1. The A1 has coefficient 1. Like if A1 had a coefficient 3, for example, then it would be coefficient 3 in here. It would be 3 coefficient 3 in here. So it would be 3K. So it would be, 3 in here, right? So basically, whichever coefficient is at like AN, that's the thing that comes in here. Yeah, and then you basically have coefficient 1 here. So you take 1 minus P1 minus P2 minus PS, right? So it's going to be 1 BN here. Okay, so this is nice. So I guess from here, what am I going to get? So from here, you just get K right away. So if you want, to compute K, you see that K is just going to be T divided by 1 minus P1 minus P2 minus PS, right? So this is what your K is. So you can, compute it easily. So yeah, so you can compute K very easily. And then what are you going to do? So then after you're done computing K, you can work with the B's, right? So now you can go back to your homework with B. So if you take all this equation, you can basically solve it, right? Which is basically this equation, which is whichever you want to do. So this equation, you can solve it. You can use this guess Bn lambda to the n. You solve it, you're going to get n root. So you're going to get something like this, that, Bn is going to be equal to C1 lambda 1 to the n plus C2 lambda 2 to the n plus, Cn lambda, or like Cs lambda s to the n, right? So you're going to get a solution like this. And how are you going to figure out what the coefficients are? Well, you're going to need the starting conditions, right? So the starting conditions are going to be, what are the starting conditions? Starting conditions are going to be A0, A1, all the way until like AS minus 1, right? So these are going to be or maybe, I don't know, maybe you want to start with A1. So A1, A2, all the way until AS. So these are going to be your starting conditions. But what you can do is you can do minus K, minus K, minus K. So if you do minus K, then what you end up getting is this is the starting conditions for B. You're going to get B1, B2, all the way until like BS, right? So you get a starting condition for S. Okay, so you have the starting condition for S, you plug them in here. So you can figure out what BN is, right? So BN is going to look something like this. And then if you wanted AN, you can just rewrite. You can just say that, well, this BN is going to be what? This BN is going to be, AN minus K, right? So you can just write AN minus K is equal to this. So you just say this is equal to this. So you can do what you can do is you can come and add plus K in here, and then plus K obviously in here, and then plus K, right? So, okay, so basically this is what your AN is. So if you look at like all this thing in here, all this thing here is AN. So basically solve the normal equation that doesn't have the constant, and then you need to add back the extra K. How do you figure out what transition you should do? Well, it comes from this equation. It's going to be this extra T that you add divided by 1 minus the coefficients, right? Or I guess the sum of the coefficients, because, P1, P2, P3, they're negative, but these are the coefficients, minus P1, minus P2. So basically take T divided by the sum of the coefficients, that's your K. So that's the K that comes in here. So, okay, so now we are done. So we know how to solve, this equation here. This one is also good. And I guess it can have multiple terms in here, right? Not only like two of them, it can have multiples. It's just like the thing is you need to transition. So basically you need to transition. Basically you do what? You do, AN is equal to BN plus K. So you need to do this transition and then solve BN normally. Okay. All right. Cool. All right. So now the next thing. So I guess there's one more thing in here. So we don't have that. Because we're going a bit over time, but let me just briefly like give you an idea of like what is going on in this case here. What if lambda 1 is equal to lambda 2? What is the big issue here? So if lambda1 is equal to lambda2, I guess let me write down an equation that has sort of like that example. So let's say 2 is a double root. So I'd have, x squared minus 4x plus 4. So I would have an equation that looks like this. So let's say that an is going to be equal to 4 an minus 1 minus 4 an minus 2. Okay, so let's imagine that I had this equation and maybe it has some starting conditions. So maybe, like a0 equals 0, maybe a1 equals 1, whatever. Some starting conditions we'll talk about them later. So let me not write what the starting conditions are. Okay, so if I had this equation, right, how would I solve this equation? So normally, I just write, an equals lambda to the n. So I just do the guess. So an equals lambda to the n. So I just take this and I plug this in here. So what would I get? Well, I would get, lambda to the n is equal to, 4 lambda to the n minus 1 minus 4 minus 4. So if I were to simplify this, right, lambda to the n minus 2 here. Right, so if I were to simplify by lambda to the n minus 2, what would I get? I would just get, lambda squared minus 4 lambda plus 4 equals 0, right? And then if you look at this, what is delta here? Delta is going to be equal to 0. So this is actually a perfect square, right? So like lambda 1, lambda 2 are going to be just 2. So basically, you can see that this is going to be a perfect square. This is going to be just like lambda minus 2 squared, right, is equal to 0. So basically, there's going to be two roots, lambda 1 and 2. They're going to be just basically equal to, 2 and 2, right? So both roots are going to be 2 and 2. Okay, so this is basically very, very, very problematic here, right? Because what would be my solution? So I guess in this case, if you wanted to compute my an normally, I would just write, that basically, an is going to be equal to c1 lambda 1 to the n plus c2 lambda 2 to the n. So let's call this is just both the same lambda, right? So then basically what I get is just going to be c1 lambda to the n plus, well, so basically this is just going to be, c1 plus c2. And it's the same lambda, right? Lambda 1 and lambda 2 is the same lambda. So you just get lambda to the n. So basically what you get is that now let's call c1 plus c2 some constant. So it's going to be c lambda to the n. So you see there is only one degree of freedom. So basically what this is saying is that an has to be c times 2 to the power n. Now this is bad because, well, what if I started with a sequence that was, let's say that the sequence was 0 and 1, right? So what if my sequence started with 0 and 1, right? A0 is equal to 0, A1 is equal to 1. Then this would be problematic because this wouldn't have any solution, right? If you were to write this down, if you were to write, A0 is equal to, well, A0 is equal to what? So A0, you see this is just going to be equal to C, right? 2 to the power 0. And then A1 will just be equal to C times 2, right? So what do I hit? So I see that A0 is going to be equal to 0, but A1 is going to be 2C, which is going to be equal to 1. So you guys see that this is a problem? Because on one side, from here, C has to be equal to 0, but from here, C needs to be equal to 1/2. So the thing is that we know what is going on. Turns out there's like no solution here, but well, clearly there's a sequence that works. If I start with 0 and 1, I plug in, I'm gonna get like 1 minus 0. So I'm gonna get 4 minus 0. So I'm gonna get to the next term in here. So if I keep computing, I'm gonna get that A2 is gonna be equal to 4. And then if I plug in 16 minus 4, I'm gonna get 12. So I'm gonna get that like A3 is gonna be equal to 12. So you can clearly see and compute them. You can start with 0, 1, 4, 12. So there's clearly something going on. So it turns out that what is the problem here? Well, the reason this equation doesn't have solutions is because, well, there is only one degree of freedom, right? There's only one option that you can pick for C, but there's two starting conditions. So because there's two starting conditions, it means that, okay, this is going to be a good sequence. If I look at the sequence, if I start with this sequence 2 to the power n, so if I look at the sequence that's 2 to the power, so if I look at this sequence 2 to the power n, so this is going to be the sequence that's basically 1, 2, 4, 8, 16, 32, da, 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 da. Well, this sequence is going to be fine. It's going to satisfy this relationship. It's a good sequence, right? Good sequence, but it doesn't satisfy the starting conditions. It doesn't have the starting conditions, right? So the thing is, basically, this is a good sequence, but we need one more good sequence. So now this is gonna look like magic, but there's basically one more good sequence, but it doesn't satisfy this. But there's one more good sequence, which is the sequence n 2 to the n. So now I'm not gonna explain why this is the case, but turns out that this is also gonna be a good sequence. So if you, for example, look at 1, and then you look at like 2 times, well, so if you plug in n equals 0, so if you plug in n equals 0, so if you plug in n equals 0, you get 0. If you plug in n equals 1, you're gonna get 2. And then if you plug in n equals 2, you're gonna get 2 times 4, so you're gonna get 2 times 4, and then 3 times 8, and then you're gonna get 4 times 16, and then you're gonna get 5 times 32, and then da, 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 da. So basically the sequence n times 2 to the n, turns out this is also gonna be a good sequence. So we can actually check it, but just believe me, guys, that like this is gonna be a good sequence. So now if this is a good sequence, I guess the more general solution that you can write is that you can say that, hey, you know what? So both of these are good sequences. Well, this one is clearly good because we already saw. So now if you were to look at like what is gonna be an, you can write down the final solution for an. So you can basically say, this thing in here, you can say that, if I wanted to compute an, then basically an can be written as like, C1, the first two good sequence, 2 to the n, plus C2, the second good sequence, n times 2 to the n. Or basically more generally, if you have two solutions, so the solutions are going to be, this is going to be, lambda to the n, and this is going to be n lambda to the n. So basically you can write it like C1 lambda to the n plus C2 n lambda to the n. So basically this is how your sequence is going to look like. So whenever lambda is a double root, you're going to write the first one is going to be normal, but then the second one is going to have like an extra term of n in here. Okay, so I'm gonna maybe take 5 more minutes, and then we'll probably wrap up class. Okay, so maybe we can do an example with this, like double root. So I think Brilliant is also good in regards with like this double roots in here. So if we look at repeated roots in here, right? So if we look at like this equation, yeah, the one that we just solved in here, right? Then what do we have? So this is exactly the equation that we had. The sequence starts off. Okay, so I just came up with it, but it's exactly the same. So if you have this equation, you see that, 2 is going to be a double root. So you're going to get n and 2 to the n, right? So actually, I guess if I were to look at, let's just look at our whiteboard here. So, okay, so what are going to be the roots? So this is going to be this sequence and this sequence. So I guess if I were to look at like my an, so I would just write, that an is going to be, C1 lambda to the n plus C2 lambda, sorry, not C2, but yeah, plus C2 and lambda to the n. So now if I were to plug in lambda equals 2 is a double root, and then, A0 is equal to 0, A1 is equal to 1. What do I get? So I'm just going to get like an is going to be equal to, 2 to the n C1 plus n 2 to the n C2. So let's just plug in n equals 0 and n equals 1. So if I plug in n equals 0, I'm just going to get that A0 is going to be equal to, I guess, C1, right? So, but A equals 0, A0 is just 0. Okay. So, okay, C1 is equal to 0. So it just means that this term disappears. So basically now an is going to be equal to, so, okay, so an is going to be that. So, okay, so now if I look at like A1, what is going to be A1? Well, A1, we just say that this term disappears, right? It's not here because, so if I plug in 1, I'm going to get 1, 2 to the 1 times C2. It's going to be equal to 1. So I guess I can just say that C2 is going to be equal to 1/2. Okay, so then I just get what? I get from here that an is going to be equal to, I guess, 1/2 and 2 to the power n. Right? Okay, so that's it. So basically this is my sequence. And now you can plug in values. Plug in n equals 0, you get 0. You plug in n equals 1, you get 1. You plug in n equals 2. What do I get for n equals 2? So A2, well, A2, I just plug in 2. 2 is going to cancel. So I'm going to get, 4. And now if I look at like, what, do I have a mistake in here? Maybe I do have a mistake. So n equals 0. So n equals 1. I'm going to get n. 2. So I'm going to get 1, 2 to the 1, C2. So this is equal to 1. So C2 is going to be equal to 1/2. Yeah, I think it looks fine. So if I plug in n equals 3 in here, right? So I'm going to get 8. So look at this. So if I plug in 3, I'm going to get 8 times 3 divided by 2, right? So 8 times 3 divided by 2, I get 12, right? And if I plug in a equals 4, so if I plug in 4 in here, I'm going to get, 16 times 4 divided by 2. So 16 times 4 divided by 2, I'm going to get, 16 times 4 divided by 2. So I get 32, right? So actually, if you look at these numbers, 0, 1, 4, 12, 32, if you were to look at like what we computed, 0, 1, 4, 12, we guess we didn't compute them, but you see that they match exactly. So basically this formula that we had in here, it's fine. So this formula is like, it's a good formula. So n equals C2 and lambda n. Okay, so now let's maybe discuss one more thing. So why is this n 2 to the n a good sequence? Why is n lambda to the n a good sequence? Why is this a good sequence? Well, let's prove it more generally. So more generally, the way this works is if you have, an, so let's say that an was equal to p an minus 1 plus q an minus 2. right? Then I can plug in n is equal to lambda to the n. So I get what? I'm going to get lambda to the n is equal to p lambda to the n minus 1 plus q lambda to the n minus 2. So if I were to simplify this thing in here, I would get, lambda squared minus p lambda minus q equals 0. So now what does it mean? I guess if I were to compute delta in here, what is delta? Well, delta is going to be b squared minus 4ac. So it's going to be 4. So it's going to be p squared minus 4ac. So it's going to be 4. So it's going to be plus 4q equals 0. So if I were to be in the case where delta is equal to 0, right? Then there needs to be a relationship between p and q. So the relationship is this one, that, p squared plus 4q is equal to 0. Okay, so what would be the roots in here? I guess if I wanted to compute lambda 1, 2, this would be equal to, I guess, minus b, so it'd be plus p. So it would be plus p plus or minus square root of delta divided by 2. Well, look at delta. Delta is 0, right? So I can just forget about delta. So it's just going to be p divided by 2. Okay, so now what did I say? I say that n lambda to the n is a good root. So basically I say that if I take, an equals n lambda to the n is a good solution, right? So, well, what's happening if I take this and I plug this in here, and in here? Let's check that it works. So if I were to do that, I would get what would be an. So it would be n lambda to the n. Let's check that this is true. So I plug in n lambda to the n. Let's check that this is true to p n minus 1 lambda to the n minus 1 plus, q n minus 2 lambda to the n minus 2. Well, if I were to simplify all the lambdas, simplify the powers, right? So if I simplify the powers, this would just disappear. So this term is just disappear. This would just be power 1, and this would be just power 2, right? Okay, and now let's replace what is lambda. Lambda is p divided by 2. So I can just write this like n. P divided by 2 squared is equal to p n minus 1 times lambda, which is also p divided by 2, plus, I guess, what is q? Now look at q. From here, you can see that q is going to be equal to minus p squared divided by 4. So let me do minus p squared divided by 4 in here. So minus p squared divided by 4 and minus 2. Okay, so now what do you guys see? All the p's are going to cancel because all have p squared. So I can cancel this p squared with this p and with this p squared. And now multiply everything by, let's see, what do I need to multiply everything by? I need to multiply everything by 4. Let me see if I get the right result. Yeah, so if I multiply, so now see, because this is division by 4. So if I multiply everything by 4, what do I get? I'm going to get, 4n. So sorry, actually, if I multiply by 4, well, actually, I can cancel. Well, there's actually this 2 in here and this 2 in here. So actually, I can cancel actually more stuff. So if I multiply everything by 4, what am I going to get? So I multiply everything by 4. I'm going to get, I guess, n, right? Because the 4 is going to cancel with a 2. Is going to be equal to 2n minus 1 minus n minus 2. And now look, guys, if I open up the parenthesis here, what do I get? 2n minus n is n, and then 2 minus 2. You guys see? This is exactly true. This is correct, right? So this is correct. So this kind of like works like magic. Basically, a, which is n lambda to the n, works like magic, because if I plug it in here, I'm going to get the green equation. And the green equation has nice properties that lambda is p over 2 and q is p squared divided by 4. So if I plug in the values for lambda and for q, and if I simplify them, I just get this thing. So it means that this is a nice solution. So basically, an equals n lambda to n works. Okay, cool. So I guess we explained what happens in here. Okay, so we explained what happens in here. There's only one more thing. What if I have a triple root? So what happens if, I had a cubic? So, what if I had an equation, let's say that an plus, and let's say that I had, p1 an minus 1 minus pa2. So minus p2 an minus 2 minus. So basically what I'm trying to say is like, what if I had a cubic, right? So an is equal to p1 an minus 1 plus p2 an minus 2 plus, p3 an minus 3. And let's say that, I had this equation. Well, again, same story, take an equals lambda to the n. And now if you simplify all of this, you're going to get lambda to the n. It's going to be, well, and again, you're going to simplify lambda, right? So you're going to get basically lambda cube is going to be p2 lambda squared plus, p1 lambda squared plus p2 lambda to the 1 plus p3, right? So you're going to solve this and you're going to get the cubic. So there's going to be 3 roots in here, lambda 1, lambda 2, and then lambda 3. So now let's say that all these roots are the same lambda, right? So if all these roots are like a triple root, if I were to solve this and I see that this is like a perfect square, perfect cube, right? Then I could have like triple root in here. Then what would happen? Then basically you'd say that, an. So the way you would write this is you'd say that, an. So there are going to be good sequences. What are going to be the good sequences? So, well, it's kind of like weird, but this is how it's going to work. So an, so you're going to have the good sequence lambda to the n. And then we saw that n lambda to the n is also a good sequence. And turns out there's going to be one more good sequence, which is going to be n squared lambda to the n. So the way you can think about this is that this one is just n0. And actually, if you had more roots, if you had, like all the way until like lambda k, if you had more roots, then this would just like, keep going down like n to the k, lambda n. So this would basically, like the roots would be like this, n to the 0, n to the 1, n squared, and then all the way until. So if a root repeats k times, you'd write like this, sorry, k minus 1. So this would be k minus 1. Right. So basically, I guess your solution is going to look like this. So you're going to say that, in this case, an is going to be equal to, c1 lambda to the n plus c2 lambda. So it's going to be c2 n lambda to the n plus then c3 n squared lambda to the n, right? And then you may have like more terms, like basically ck n to the k lambda to the n. If you want to have more terms, but you guess you can just like stop at 3. So 90% of the time, you're only going to have two roots. Maybe 5% of the time, you're going to have this. And then maybe 0.001% of the time, you're going to actually have this extra term here. So I guess this is how it generally looks. So I guess we kind of like also answer the more general question when you have triple roots. What if, lambda 1 equals lambda k, right? And then we saw what is happening. So basically, if I were to simplify this an would be, so if I just write it down, an would be equal to what? It would be equal to c1 lambda to the n plus c2 n lambda to the n plus, c3 n squared lambda to the n plus, it have ck n to the k minus 1 lambda to the k, right? So this is kind of like what happens. Okay, so this is kind of like the general, overview of like all these topics. And then I guess the next thing is you can do practice problems, right? So the practice problems, again, Brilliant is a good resource. It has a lot of problems in here. It has stuff with, for example, like what is happening when you have double roots in here. So for example, you have double roots, you see this one, and then you can have, for example, triple roots, right? Okay, so now I guess the final question is like, let's imagine that this is the last step, and then we're gonna end here. Let's imagine that, I had a sequence that's like a really big sequence. So let's say maybe it had 10 terms, right? So, it maybe had something like this, that, an was equal to, I don't know, like P1 an minus 1 plus P2 an minus 2, let's say P10 an minus 10. Okay, so there's going to be 10 roots in here. So what are going to be the roots? So let's say that maybe the roots lambda, these are going to be the roots. So let's say maybe the 2 is a triple root. So maybe 2 is a triple root. So I'm going to have, the roots are going to be 2, 2, 2. And then maybe I'm going to have, 5 plus 6i, and then I'm going to have 5 minus 6i, right? So I'm going to have like two complex numbers. So, well, actually, instead of writing them like this, maybe I should write them. So if they're going to be complex numbers, write them like this, like, maybe this is going to be 3e to the I 30 degrees. And maybe it's going to be 3 times e I to the minus 30 degrees, right? Okay, and then you can keep going like this, right? So maybe, I don't know, maybe I'm going to have another root that's, I don't know, 1 plus square root of 3, and then also 1 minus square root of 3, and then, I don't know, maybe there's like more roots in here, and then maybe 7 is also a root, and Well, then what is going to be, your an? So if you wanted to compute an, then you'd get that, an would just be equal to what would be c1 times 2 to the n plus c2 times n 2 to the n plus c3 times n squared 2 to the n, right? So this is like the three roots in here. And then what about the next two? So this two would be combined as like sine and cosine, right? So you'd write, it's like 3 to the n, and then you'd write, like d1 cosine 30 plus, d2 sine 30, right? Okay, so you've got this thing. So eventually you're gonna need to plug in, you're gonna be given, so because this looks like 10 terms back, you're gonna be given some starting conditions, right? So starting is gonna be like A1, A2, all the way into like A10. So you're gonna need to take this like 10 starting conditions, plug them in here and solve. Right. So then actually we're not quite done here. Because there's like more terms. There's gonna be this terms, right? So it's gonna be, maybe actually I should have called this C4 and called this C5. So it's gonna be like, C6. And then 1 plus square root of 3 to the power n plus c7, and then 1 minus square root of 3 to the power n, and then plus c8 I guess you know what's going to be C8, the last one. So C8 is going to be, let's say this one 7. So it's going to be C8, 7 to the power n, and maybe let's say the 10 was also a root in here, and the 12 was a root. So it's going to be C9, 10 to the power n, and let's say actually instead of 12, let's do minus 3. So let's say that minus 3 was also a root, and then it's going to be plus C10 minus 3 to the power n. So basically, yeah, this is how it's going to look. So if you have like something crazy, so this is very unlikely that it's going to happen, but this is kind of like the more complex case, is that like, let's say you have 10 terms back. So you have a polynomial of 10 degree, then there's going to be like 10 roots. Maybe some of them repeat 2 to 2. Maybe the 2 of them are complex. Maybe there's going to be something with square roots that are going to be like conjugate. There's going to be some normal ones. There's going to be some like negative numbers. Well, how do you do that? You just like write them like this. And then the complex numbers become cosines and sines. We're going to have 10 starting conditions. You have 10 coefficients, C1 through C10. And you write the 10 starting conditions. And then, you solve the system. And then you're going to get all the coefficients. Okay, so any questions on this so far? Yes, no? Okay. Okay, so I guess we can take a break here. So we kind of like looked for all the possible cases, right? And yeah, there's like kind of like 6 general cases. They get more and more and more complex. And I guess there's also like you can add an extra plus t in there. Well, but we know what to do if you add an extra t. You just need to convert to the sequence Bn and then solve Pn, and then add the extra k back. All right, cool. So I guess that's gonna be it for the sequences, linear recurrences part. So I guess now we're gonna like take a break here, and then the homework is gonna be basically to read through this brilliant article again, which is like really pretty good, and then also through this like book chapter from the intermediate counting and probability book, chapter number 10 that I shared with both of you in the chat. And then actually, if you have time, you see that if you're gonna go here towards the end, there's gonna be a bunch of practice problems. So you can skip the part with Catalan numbers in here. We don't need that. But you can basically try and solve all our practice problems. And then if we have time, we're probably going to like discuss linear recurrences in more detail. All right, cool. So any questions? Yes? No? All right, then we'll take a break here. Thank you everybody for joining, and happy problem solving.